Dastidar teaches at Department of Economics as an associate business economics as an associate professor in the South Campus, University of Delhi. A highly acclaimed teacher who has done her MA, MPhil, PhD from JNU. She has great interest in research in the areas of international economics, economics of development, particularly problems of poverty and income inequality in developing countries. She specializes in macroeconomics, econometric methodology, and Indian economics. Dr. Ananya Dastidar has been teaching for more than 2 decades. And I'm sure, friends, she is going to instill in you a thirst and a hunger for not just the research part, but also in terms of learning. And I'm sure that each one of you at the end of the session will go back home more invigorated, informed, and interested in these areas. Thank you so much, ma'am. Over to you.
Um, a very good morning to all the participants. So as you can see from my screen, we have a lot of things to discuss today, and we are ready to do so because we have made our groundwork, which was to understand the assumptions of the two variable OLS model, to understand some of the basic results in the two variable OLS model, so that now we are ready to talk about some of the important issues that can be taken up in the context of this model. First among these will be to understand that though we call it the ordinary least squares model or the linear regression model, it accommodates a whole bunch of nonlinear relations between the dependent and the explanatory variables in the form of log-log, semi-log models and models with quadratic terms. So at the very outset, just as we touch on this, I want to make the point that whenever I'm talking about taking log in an econometric model, in the context of a regression model, it's always natural logarithms, that is log base e, okay? Now, I'm going to start by actually running some regressions, and as we go, we are going to interpret the results and talk about all these models which can accommodate nonlinear relations. Now, till yesterday, I have been using Excel to run regressions. Now today, I will make a switch to a different program called Stata. So to begin with, I will run Stata and you will see the results. So to begin with, our focus is going to be entirely on the results and not on Stata details. I will begin the second session today by telling you the details of Stata, okay? That is how you use Stata and so on. And you will see more of that in the course of this program, right? So to begin with, I'm just making it clear that I'm not going to be discussing Stata details. I'll just be discussing econometric details. Is that clear, right? So I mean, the reason I'm saying this is don't bother asking questions about Stata. Those I will anyway be taking up in the second, so from the 12 o'clock session onwards. That's one point. Okay. Now, having kind of looked at all these nonlinear, that is log-log, semi-log models and so on, I'll move on to the multiple linear regression model, and in particular, talk about the interpretation of the results in such a model and take up something that we began yesterday. So yesterday we talked about standard errors, and we talked about how standard errors can be used to calculate t-statistics and carry out hypothesis tests using those t-statistics. So I'll come back to hypothesis tests when I'm talking about the multiple linear regression model. And then I will end the morning session by discussing the problem of multicollinearity. Okay, that's the plan for the morning. In the afternoon, I'm going to, so in the second session rather, so I'm going to take up models with dummy explanatory variables and discuss the problem of heteroscedasticity, what the problem is all about, that is the definition, how do you actually test for heteroscedasticity, and I will discuss a very simple and easy to implement fix for heteroscedasticity. Now here, let me clarify. My entire discussion in this session has been on the basis of cross-section data sets. So I therefore have nothing to say about the problem of autocorrelation. The problem of autocorrelation is something that arises only in the context of a time series data set. Therefore, in this set of lectures, I'm not at all touching on the problem of autocorrelation. However, I just wanted to flag it that, there is such a problem, and it's a problem which involves the error terms getting correlated with each other and then creating a whole range of issues. Such issues, if you are interested in understanding, you have to begin by looking at time series analysis. And as I said, I'm not taking this up right here. Okay. And again, as I said also, we are going to be using Stata today for our estimation exercises. Okay. Right. Now, let me just take you back one or two steps to make a very simple point. So this was our starting point yesterday. And if you remember, we ran a regression of wage on education using a two-variable model. We talked about the sign and magnitude of coefficients. We talked about y hat, or the predicted values. We discussed residuals. We talked about the concept of an R squared. We talked about the error variance or sigma square, and the related concept of the standard error of the regression, which is sigma hat. And linked to that, we talked about the standard error of the estimators, which are under root of var alpha hat and var beta hat. And we also talked about the statistical significance of the variables. This was the very last thing that I discussed. I said that, look, you can do hypothesis tests using t-statistics, and a high value of the t-statistic leads to a rejection of the null that the estimated coefficient is actually, the unknown parameter is actually is equal to 0. So a high t-statistic tells you that the null beta is equal to 0 is being rejected, which means that the variable in question is statistically significant. So we have seen this, and I'm going to, as I said, take this up in the context of multiple regression. Now, what I did not discuss at all, and I would like to start with that, is the interpretation of confidence intervals. So I'm going to start by telling you how to interpret the confidence interval, which is also reported with the results. And here, I would like you to take a good look at the Excel results, which I'm going to take you to now. Because what I will do is, I will then switch to Stata. I will switch to Stata, and I will run the same regression, right? And I want you to check that when you use the same data set, no matter which package you are using, you will get the same results. And just like you have several things getting reported along with your results in Excel, R squared, standard error, p-values, t-stat, confidence intervals, everything is also going to be reported in Stata. So the message that you want to get out of that would be that no matter which package you are using, the results tend to get reported in the same way. So, the point is that don't worry too much, therefore, about what package, okay? Any package. The main thing is that once you have the results, what sense do you make of those? So that's going to be the thrust of my talk throughout. So I'll start with the Excel file, which, I had been working with so far, okay? So here you are. I'll quickly show you the data. So this was our data on wage and education, and we regressed wage on education, and we got these results. So highlighted in yellow, as you can see, there is your alpha hat, beta hat, and so on. Now I want to begin by talking about the confidence intervals. So I have just highlighted this in yellow. Now you see there are these 4 numbers that have been highlighted, right? Let me start by talking about the confidence interval for education. So I'm just going to be highlighting, I'm just going to turn these letters red, okay? So when you run a regression and you get some results, you see that here is your beta hat, okay? So here is your beta hat, right? Here is the standard error of beta hat. Here is the t statistic for beta hat. Here is the p-value for beta hat, right? You see all of these. Now, what about these 2 numbers that I'm just putting in brackets? So one, as you can see, is the lower 95% confidence limit, and the other is the upper 95% confidence limit. So that together, okay, these 2 numbers, which is 0.43 and 0.64, give you what is known as a 95% confidence interval for beta, okay? So that's the first thing, the terminology. How do I know it's 95%? Because that is what is getting reported. It is saying the package is reporting the 95% confidence interval. Now, I just want to start by how do you interpret this? Now, remember, what is it that we are estimating? We are estimating beta, where beta is the effect of education, an extra year of education on wages. So beta is basically a number that I do not know. Now, I can either offer a point estimate of beta, right? Which is one number which says that, look, beta hat is equal to 0.54. So I want to estimate beta. Beta is this unknown number. And the point estimate for beta is right here, okay? 0.54, okay? So that's like saying one number is what beta hat is actually going to be. However, we know that once you change the data and so on, you'll get different beta hats. So instead of just relying on that one number, instead of relying on the point estimate for beta hat, we like to specify a range, okay? A range that is likely to contain beta 95% of the time, or with 95% probability. And which means there's a 5% probability that the range does not contain beta. So when you calculate such a range, which is reported with your results, you're really saying that there's a 95% chance that the range 0.4 to 0.6 contains the true beta, which remember we have not seen. So beta is an unknown parameter that we cannot observe. But we can say on the basis of our regression that, look, the range 0.3 to 0.64 has a high probability, 95% chance of containing the true beta. Is this correct? Now, please note, I am not saying that beta lies in the range. I am saying the range will contain beta. There's a reason for that. You see, the range itself is random. If you change your data, you will get another range, right? And how is the range calculated? The range is actually calculated as beta hat plus minus a t-value times the standard error, okay? Times the standard error of beta hat. This is how you calculate the range. So any basic, statistics book which talks about confidence intervals will tell you how to estimate a confidence interval. And the confidence interval being estimated here is absolutely no different. Okay, so so this is something that I wanted to just begin with. That whenever you are getting some results, make sure you also interpret the confidence intervals. Now, this is particularly to research scholars. Research scholars, I have seen, they will run a regression and then they will present their results. But I have never, hardly any research scholar has ever touched on the confidence interval. They're just jumping around about their point estimate and whether, we tend to ignore the confidence interval. Please don't do that. It's giving you very important information. Okay. Right. So I wanted to start with this basic point. Now, I realize you must be having questions, but I'll take questions once I've covered some ground. Okay, so questions will be taken after some time. So put in your questions as you go. Note them, and then we will collect some questions and then answer it at the end. Okay, so having hopefully clarified the concept of a confidence interval, I would now like to go to Stata and run the same regression. So I would like you to note some features. Look at the slope coefficient 0.54, intercept minus 0.9, okay, r squared 0.164, and so on, right? So let's see that we get exactly the same results in Stata. Now, when we get exactly the same results in Stata, what is that telling us? You see, it is also telling us that Stata is also using the OLS estimator. So Stata is using the same alpha hat equal to y bar minus beta hat into x bar, and beta hat is equal to covariance xy upon variance of x. The same formulae, the same estimators are being used in Stata as well. So I'm going to run a regression of wage on education, and here are the results for you to see. I will repeat. Right now, do not worry about, I don't know how to run regressions in Stata. You will learn. Hold your horses. You will learn about that. I will also tell you about this when I begin my session at 12 o'clock. I will take you through some steps. For the time being, concentrate on the results. Okay, that's a request. Okay. So here you are. I have run a regression of wage on. I have run a regression where the dependent variable is wage and the explanatory variable in education. Now, look at all the coefficients. So education, exactly the same, 0.54. The constant term is minus 0.90, just as we saw in case of Excel. And here is my R squared. Okay. Now, where is the standard error of the regression getting reported? Stata is also reporting it, but they are calling it something slightly different. Okay. They are calling it root mean squared error. Okay. So here is the standard error of your regression. So these are terms that you have to learn because different packages call them different things. You know, it also has to do with patents. So if you do call it the same thing, they will say, you know, they are copying me and so on. But anyhow, so root mean square error is perhaps a direct way of telling you what this is. This is the square root of the squared and summed residual. So that's where the mean square error is coming from. Okay. And if you had noted, this is exactly the same standard error of the regression as you saw in Excel. Now, these are the standard errors of the coefficients. These are the t values, these are the p values, and here is the 95% confidence interval. Okay, so everything is as was. All right. So no matter which package you run the regression in, it gives you the same result. Okay. Now, as I told you that I am going to be talking to you today about models with certain non-linearities, right? So let me start with a very useful kind of a model where the dependent variable is in log form, but the explanatory variable is in form of levels, okay? So we will take log of wage and regress it on education. Wage will be in log, but education remains as it is. That's why it's called a log level model. Okay. Now, let me first run such a model for you, and then we will interpret the coefficient from such a model, and we will then differentiate between the level model. So this model that I have just run, both wage and education are in their original forms, in their level forms. Okay, this is a level model, right? Now, let me run a log level model, and then we will be able to interpret that and differentiate it with results in a level model. So first, I will generate a variable called log wage, which takes log of wages. Okay, and okay, so Stata is giving me an error message. It is saying that log wage is already there. So wonderful, the data already has it. I must have done it earlier. So I am just going to regress log of wage on education. Right. Now, let us look at these results. Okay. Note the dependent variable over here is the natural logarithm of wage. How do you know that? Because you know the program has already run. Such a variable has already been generated. Otherwise, I would just have generated it. Okay. Um, those of you who have Excel, you can just generate a log of wage in the Excel file or log of any variable that you have very easily by using operators in Excel. All right, so don't worry right now about the how to do it. Concentrate on having done it. What do we have? Okay, let's concentrate on the interpretation. So when you have regressed log of wage on years of education, let us look at beta hat. Where is beta hat? Okay, so this here is beta hat. Okay, 0.0827444. All right. Now, how do I interpret this? Okay, this is telling me that for one more year of education, okay, uh, wages increase by 8.2%. That is, wages increase by 0.08, well, I just round it off, 0.083 into 100. That's equal to about 8.3%. Why is this happening? I'll just take you there in a bit. Okay. Now, this is a constant percentage effect model. Okay. Let us differentiate these results from the results that we just saw a little while ago. So when we regressed wage, so when I just regressed wage on education, what did I get? I got this. I got it that one extra year of education increases your wage by about 0.54. Sorry, it increases your wage by $0.5. Okay, that was my result. Why? Because education is measured in years and wage is measured in dollars. So an extra year of education increases wage by about $0.50 or about by 50 cents, right? That is what these results are telling you. The results in your level model where you've regressed wage on education. Now look at this model where you have taken logarithm of wage and you're regressing that on education. So dependent variable in log form, but explanatory variable in level form. What do you do here? You take your beta hat. So what is my beta hat? My beta hat is 0.83. Okay. So you just take your beta hat and then you multiply that beta hat by 100. Once you do that, which is exactly what I have done, what you get is a percentage change in wage. So you're saying that for an extra year of education, your wage is going to increase by 8.3%. Now, why is this a constant percentage effect model? Because it is saying that if your education increases from 5 years to 6 years, wage will increase by 8.3%. If it increases from 16 years to 17 years, wage will increase by 8.3%. So this is telling you that for a unit increase in education, no matter what the level of education, whether you're looking at 10 to 11 or 16 to 17 or 20 to 21, as long as you're just looking at a unit change in education, 1 year increase in education, wage will increase by 8.3%, the same percent. That's why it's called a constant percentage effect model. Whereas what about the level model? This was telling you that every time that you increase education by 1 year, your wage will increase by 50 cents, right? So I hope you see that we always tend to prefer such models. A model where the dependent variable is in log terms. Because I think it is somewhat more realistic to say that, you know, your wage will increase by 8.3%. Because percent is taking into account the base. So no matter what your wage was to start with, you have a 8.3% increase, right? Whereas this model, the level model is just saying that no matter what your wage was, it is just going to keep on increasing by 50 cents every time you get a 1 year increase. So in terms of interpretation, we tend to prefer running models with the dependent variable in log forms in many cases, okay? Because it's giving us this percentage effect. Now, how did I get this? How did I get this beta into 100 and so on and so forth? So to understand the interpretation of coefficients in models with non-linearities, in models with log, etc. Terms, let me take you to some theory, because that will help you understand. And you know, something very basic that we started with is where we now have to go back to. What did we start with? If you remember the first day, you know, that I had a session with you on Monday, I started with the straight line. I started with the slope of a straight line. So you see, we said that, look, the slope of a straight line can be captured by such a term, dy upon dx, right? Okay. So what I'm going to tell you is the following thing, that whenever we are running a regression, what are we saying? We are basically saying that, look, the dependent variable is a function of x, right? We are saying this. And what is it that we are interested in? Why are we running this regression? We are really interested in finding this. We are really interested in asking, so what is dy dx? Invariably, whenever you are running a regression of y on x, what you are after is dy dx. Please keep this in your mind. It is a simple point, but it is a very important point, as you will just see. Okay, so let me now take you to trying to understand what is it that that is going on when we are talking about you know, interpreting coefficients from a nonlinear model. Okay, right. Oops. Okay, so as I said, so rather, you know, the so what we started with was this this particular thing, right? We ran a regression of log of a dependent variable on a explanatory variable called x, right? So the dependent variable is in log form and the explanatory variable is in level form. And this is my error term. So epsilon, you know, I mean, in a hurry, maybe I've made a little bit of there's such certain lack of uniformity in the notation, but epsilon also denotes errors, okay? U, epsilon, all of these denote errors. And alpha or beta naught, both of these denote the constant term, okay? So I will just clarify that once again. So this is the basic model where log of y is equal to beta naught, which is the intercept, beta naught or alpha, same thing, plus beta 1 into x. So beta 1 is the slope coefficient and x is the explanatory variable. Now, when you are, so if you look at equation number 3, when I estimated the log model, I basically am estimating equation number 3. What am I doing? There is a non-linearity here. You see the non-linearity is right here. Look at equation 1. It means that y is e to the power beta naught into e to the power beta 1x into e to the power epsilon. That is what you are assuming each time that you are running a regression model with the dependent variable in log form. Remember, I told you this is log based E. So essentially, your model is this one. This is your model. Y is equal to e to the power beta naught plus beta 1x plus epsilon. Okay. So when you take log, you linearize the model, you linearize this particular non-linear model, and then it just fits into the OLS framework. So now we just put it into the framework that, okay, y is equal to alpha plus beta x plus u, where what is my capital Y? My capital Y is basically nothing but log of small y, where small y is my dependent variable. So capital Y is log of wage, and wage is of course small y, all right? So this is something you have to understand. Every time that you are running a regression with the dependent variable in log form, your underlying model is essentially this. So some of the points that I want to flag over here are the following. In your OLS model, once you fit this model into the OLS framework, so equation 3 is being estimated using OLS, the disturbance term enters as with a plus sign. It's additive. But in the original model, that is in equation number 1, so let me just make this point once. So in equation number 3, the dependent variable is additive, but in equation number 1, which captures a nonlinearity, the error term is multiplicative. Okay, this is known as the multiplicative disturbance formulation. So originally y is equal to e to the power everything, e to the power the constant term into e to the power beta 1x into e to the power of the error term. Okay, error term or the disturbance term, same thing. All right. Okay. So this is something that I wanted to show you right at the outset before we go on to interpreting the result. So what is the point here? The simple point here is what you are doing when you are incorporating non-linearities in the OLS framework. Okay. All right. So let's move on. Now, we just looked at a log level model like this one, okay? So this is my log level model where log y is equal to beta naught plus beta 1x plus the error term. Now, how do I get, so now what am I trying to do? I'm trying to get you to understand that when you have estimated such a model and you've got your beta, how do you interpret the result? How will you go about this? You will actually take total differential of both sides of this particular equation. Once you do that, basic calculus tells you that the differential of log y, because now our dependent variable is log y, is 1 upon y, right? So on the left hand side, we will get dy upon y, dy upon 1 upon y, okay? And on the right hand side, we simply get beta 1 into dx. So of course, we are working with the model in averages. So the errors are mean 0, that's gone. And beta naught is a constant. So when you differentiate, that also goes away. So please have a look that when you take total differentials of both sides of this, you actually end up right here, okay? D of log y, which is dy upon y, okay, which is right here on the left hand side, is equal to beta 1 into dx. Now just multiply both sides by 100, okay? Multiply both sides of 2 by 100 and look at what you have. So here you have dy upon y into 100. So what is dy? Small change in y. Y is the base. So what you get is a percentage change in y. So the left hand side is a percentage change in y. What is the right hand side? Right hand side is your beta 1. And mind you, now beta 1 is multiplied by 100 because this has been multiplied by 100. Okay. And you have dx. So dx is a small change in x. Okay. Right. So let us now put the small change in x as equal to 1. Right? Let's put dx equal to 1. Then what are we left with? We are left with dy by y into 100. So we are left with dy by y into 100. Sorry. We are left with this term, which is a percentage change in, it's an approximate percentage change in y is equal to beta 1 into 100. Why? Because dx is equal to 1. All right, when dx is equal to 1. So what does this give you? Beta 1 into 100 is basically the percentage change in y for a unit change in x. Why unit change? Because this is dx. All right, I have not done anything to the explanatory variable. Okay. All right. Okay. So this is where you get the background from. Now here you see I have got another sort of result for you to interpret. Now, suppose I take some data on CEO salaries. Remember, I had shown it to you. So, CEO salaries and firm sales, cross-section data. So, I have data on, let's say, 500 firms. For each firm, I have how much they are paying their top boss, their CEO. And for each firm, I have data on how much is their total sales over that period for which the salary is being reported. So, I want to check whether firms that are very large in terms of sales pay their CEOs much more. Okay, so I have this data. Imagine I have the data. So I'm using that data on CEO salaries measured in $1,000, regressing it on firm sales, except I'm now regressing log of salaries. So suppose I run a log model. Log of salary regressed on sales, not log of sales, mind you, sales. Okay. Now I get this result. So log of, so I'm calling this log of y hat because that is what gets predicted. Okay. Log of salary hat is going to get predicted. So log of y hat is equal to, let's say 6.84, that's the constant term, into, so this 1, 2, 3, 4, like 4 zeros, 0.000015x. X is sales. How will I interpret this coefficient? Look at my rule. I will take the beta hat, right? So I will take this 0.0000 1, 2, 3, 4, 1, 5 and multiply it by 100. Right. So why am I doing that? Because that's what I just saw. Right. So whatever I get, which is this particular term, all right, is the percentage increase in CEO salaries for a 1 unit increase in sales. So if you look at this particular result, it is telling you if sales increase by $1 million, unit in which they have been measured, then CEO salary is associated, will increase by 0.15%, sorry, 0.0015%. Okay. Now, there are several things I want you to note over here. First of all, please see, I'm not saying that a 1 unit increase in sales is causing CEO salary. You can't say that. On the basis of a regression model, you can say nothing about causation. All you can say is about association. So then, am I saying that, oh, then you can't say that, more sales actually give you higher salaries? Of course, you can say that. But you can't say that on the basis of the regression model. You will have to say that on the basis of theory. So of supreme importance is theory, the context. So your understanding of a theory, your understanding of a context will tell you what is the dependent variable and what is the explanatory variable. So that is something you have to remember, okay? And what the regression result will be giving you is the fact that a certain change in X is associated with a certain change in Y. It's going to give you the dy dx. Basis that you can't claim causation. Causation has to come from your background, your context, your theory, okay? So let me just repeat that once more. So I have regressed a dependent variable in log form on an explanatory variable in level form, okay? And so the explanatory variable, as you can see, is in level form, okay? And how do I go about interpreting the result? I take the beta hat and then I multiply it by 100. What does that give me? It gives me a percentage change. Okay, it gives me the percentage change in Y for a unit change in X. Now look at this result over here. Not nice, no? You don't like to report things with 0.0015%. It sounds very bad. Like it's so less and all that, right? So fine, don't report such things. Be clever, all right? Scale up your explanatory variable. Don't talk about a $1 million increase in sales. Talk about a $100 million increase in sales. Multiply beta hat by another 100. So you're now saying, suppose dx is equal to 100, right? Then what is then what will this thing be? This thing will simply be beta 1 into 100 and then into another 100, right? So $100 million increase in sales is associated with a 0.15% increase in CEO salary. So CEOs get so much salary, right? I mean, even if they get a 0.15% increase, that's pretty good. All right. So in terms of your results, that's a better result to be showing. So please be clever about these things, right? Remember, I told you that when you're interpreting coefficients, we care about the sign. This has the right sign, so it's positive. As sales increase, so firms with larger sales pay their CEOs more. That's fine. That's expected. But also the magnitude matters, right? So when you're getting when you're getting these sorts of results, so many zeros in front, if the results are correct, right, then you just scale up your explanatory variable, scale up the change in dx that you're talking about and report results that look better, okay? Right. Okay, so this takes care of one kind of model that we just looked at. Okay, now let me look at a different sort of a model, which is a log-log model. How do I interpret coefficients on such a model? So when we have a log-log model, okay, as in this case, so we are still talking about, okay, we should put, yeah, so I wish I could, yeah, all right. So now I'm talking about estimating coefficients from a log-log model, okay. What is that? This is a model where both my dependent variable as well as my explanatory variable are both in log form. So think of me regressing log of CEO salaries on log of sales. Now what will you get? So again, how do we interpret such a model? We take total differential of both sides. So look at how I am proceeding. What is my goal? My goal is ultimately the divide dx, all right? So we have to get our model down in divide dx form because we want to figure this out. How does y change, or what kind of change in y is associated with a certain change in x? So you take total differentials of both sides. Remember that both variables y and x are now in log form. So both will, when you're differentiating it, will get divided by the respective value. So d of ln y will be 1 by y, dy by y, and d of ln x is going to be dx upon x. So you have a dy upon y and a dx upon x. And of course there is the beta because the rest of it just vanishes. So now what do you have? Now you see, if you are multiplying both sides by 100, then you are getting a percentage change on both sides, right? And of course, you know, this 100 will get cancelled. So beta 1 is basically dy by y upon 100 into dx by x upon 100, and the 100 gets cancelled. So what are you left with? What is beta 1 capturing? Beta 1 is now the percentage change. So remember, it's an approximate because it's dy upon y, right? Small change upon y. So it's the percentage change in y associated with a 1% change in x. So I put dx by x equal to 1. Okay. So I'll just repeat that. So when you have a log-log model, what is your beta 1 giving you? Beta 1 is itself giving you a percentage change in y associated with a 1% change in x. Okay. Associated with a 1% change in x. All right. So why 1%? Because I'm just putting dx by x equal to 1. All right. So the main point is that you do not now have to multiply beta 1 by 100. Beta 1 itself is giving you a percentage change. Okay. Right. So let me quickly repeat this. So I will take you to the data. Let me just go through the theory a little bit, and then we will go to the data, and we will estimate these models, and we will see how to interpret the terms. Okay. So just wait for like a few minutes. So first of all, let me just compare quickly what I have just done. I have told you that, look, when you have log level model, okay, so dependent variable in log but explanatory variable in level. When you have a log level model, what do you have to do? You have to multiply beta 1 into 100. If you do that, that gives you percentage change in y for a unit change in x. Okay, but if you are estimating a log-log model where both the y and x are both in log forms, then you don't have to multiply the estimated coefficient to get a percentage change. Itself, it is giving you a percentage change. Okay, it's telling you what is the percentage change in y, which is associated with a 1% change in so beta 1 itself is the percentage change in y associated with, right, a 1% change in x. Okay. So if you remember, I told you that we are going to talk about semi-log models and log-log models. So I have talked about the log-log model. This on my screen is a log-log model and how to interpret the coefficient. And I've talked about one kind of a semi-log model, which is a log level model, dependent in log, explanatory in level. There's one other kind of a semi-log model. So a semi-log model is one where some variables are in logs and others are not. Okay. So a different kind of a model is this one, where you see, we'll call it a level log model, because a dependent variable is in level, but the explanatory variable is in log. Now, by the way, I'm taking you through this because, I want you to get the trick. What is the trick? Any model that you are estimating and you're wondering how I'm going to interpret the results, right? Which, by the way, is the most important thing. You don't have to do anything. Package will do the doing. You have to do the interpreting, right? So that is really the main thing, the main game. So how will you go about it? That is what I'm trying to, give you the hang of. Okay. Remember that your objective is dy dx, right? So just work in towards that end. My objective is dy dx, right? What is the change in y associated with a small change in x? So how will I proceed now when my dependent variable is y, but my explanatory variable is log x? I will again take total differential of both sides. I will realize that this is what it gives me, that log of x is going to be x upon, dx upon x, so that I will get this kind of a term. So I've just taken dx on the other side. Okay. So now this can also be written like this, right? So you take total differential of both sides. So dy is equal to beta 1 upon x into dx, right? So I'm just rearranging the terms. What am I doing? I'm just multiplying and dividing the right hand side by 100, right? So multiply and dividing the right hand side y, because I'm going to get a percentage change in x. This then becomes a percentage change in x. Okay. So, so I hope what I've done is clear. All right. I'll just take you through it once again. I started off with a model where y is in level and x is in log form. I took total differentials of both sides, and then I have x in the in the denominator over here, because this is log x, basic calculus. And then what I did was I just multiplied and I divided by 100. I just divided and multiplied the right side by 100. Now look at what kind of a nonlinear model this is giving you. First of all, you see in this model dy dx is equal to beta 1 upon x. So this is nonlinear. The slope is not constant. So the relation between y and x is not, it's not like a straight line. Because here the slope dy dx is the slope of the function, right? Y is a function of x and the slope is dy dx. Dy dx itself is a function of x. What kind of a function is it of x? As x increases, given beta 1, dy dx is actually coming down. So this is a model which is actually capturing some kind of diminishing returns. Think of agricultural productivity and fertilizer. So if I'm trying to capture the effect of increasing fertilizer use on productivity, this is an ideal model to be using. You regress productivity on log of fertilizer, because that's going to capture the effect of, as you keep on increasing fertilizer, productivity will increase, but then as beta 1 is fixed, right? But as your x keeps on increasing, there is going to be some the increment is going to be at a decreasing rate. So the slope is going to keep coming down. The slope is not constant. If I have a level model, the slope is a constant. Dy dx is equal to beta 1, no matter what is my level of x that I'm considering. But here the level of x has a bearing on the slope. As the amount of x, as the amount of fertilizer keeps on increasing and increasing, the incremental productivity from extra fertilizer is going to keep coming down. That's the sense in which this model is capturing some kind of diminishing returns. That's one point. Now, what is the other point? The other point and the main point is that if you have estimated this model, y on log x, what do you do with your results? So you see, what you do with your results is going to be over here. So this is just me multiplying with and dividing both sides of this equation by 100. Not both sides, sorry, just the right hand side. So that, you know, it makes no difference. So here, look at the left hand side of equation number 4. The left hand side gives unit change in y. And what does the right hand side give? The right hand side gives percentage changes x. So suppose I say 1% change in x, then what am I getting? I'm getting dy is equal to beta 1 upon 100. So now you divide your coefficient by 100. So beta 1 upon 100 gives you the unit change in y for a 1% change in x. Clear? So basically, it's not that difficult at all. All right. So okay. So you see another small point, but again very important point is that whenever you are working, always work from what I like to say, what my teachers have told me. I've been fortunate to have an excellent set of teachers. So my teachers, especially from my masters onwards. So you know, my teachers always told me that work from first principles. Okay, so this is something I also want to tell you. So, you know, whenever you're working with something very complicated, begin at the beginning. Okay, so if we begin at the beginning, then we see that things are not at all very difficult. They can be worked through. So here we have a model where I'm regressing y on log x. When I take total differentials, I realize that this can be written down in the form where I express a unit change in y for a 1% change in x. And what captures it? Beta 1 upon 100. My estimated coefficient divided by 100. So if we look at that data, right? So if we now regress CEO salaries, so CEO salaries in 11 on log of sales, okay? So we're now taking log of the explanatory variable. And let's say I get this model. What is this saying? So remember, this is, I have to take beta hat and divide it by 100. Now, which is exactly what I have done. When you divide beta 1 by 100, you are getting 2.629. And what is that? It shows that a 1% increase in sales. So now the explanatory variable is a percentage change. So 1% increase in sales is associated with a $2,629,000 increase in CEO salaries. Okay. So now this 1% increase in sales is coming out of this thing being equal to 1. Now we don't like to say $2,629,000. Why am I saying that anyway? Because I know that CEO salaries are measured in $1,000. So I will just multiply this with 1,000 and say that it increased by $2,629. Okay. Right. So I will just take you back to my very first slide and just wrap up what we have just learned. When we are estimating a log-log model, take the reported beta hat, that itself is a percentage change. It's the percentage change in y for a 1% change in x. Do nothing with it. बस उठाओ, वही है percentage change. ठीक है? Log-log model. Both y and x in log. Now, suppose I have a semi-log model. Then it depends what kind of a semi-log model. Suppose I have a semi-log model where I'm regressing log y on x. Then take the beta, multiply it by 100. What is it giving? It is giving what is the percentage change in y for a unit change in x. Okay. suppose I have a semi-log model where I'm regressing y on log x, right? Then what do? Take the beta, but now divide by 100. Take the beta, divide by 100, and what is it giving you? What is the change in y? What is the unit change in y for a 1% change in x? Okay. So this is, what I have to say so far as nonlinear relations are concerned. Now, I would also like to discuss a model with quadratic terms, but let me before I do that, let me now introduce the multiple linear regression model. And again, before I do that, let me first introduce the multiple linear regression model, okay? Then I will take you through some exercises, some actual regressions using log, semi-log models and so on, okay? So I will use, a certain data set, and I will do that. What should I do? Okay, maybe let's say with all this log etc. Let's finish that first. Okay, let me finish that first. Okay, I'll just see if I can quickly use a data set and do that. Okay, so what I will do is I will try and get a CEO data set. All right. So yeah. Okay. Right. I'll just find the data set. I'll just see. Yeah. Yeah, okay, here it is. So, okay. So, this is a data which looks like this, okay? I have CEO salaries for many, firm CEOs. I have sales, okay? Sales are, in millions of dollars, and I have return on equity and so on and so forth, okay? There are all these things that I have. Okay. Now, let me run a regression, which is a level regression. Now, again, for those of you who may have joined in late and are worried about, I don't know Stata, doesn't matter, you don't know Stata, you will learn about Stata. I'm not teaching Stata now, okay? I am now teaching interpretation. I will talk about Stata when I come back at 12 o'clock, okay? So don't worry about Stata. So regression of CEO salaries on sales. This is a level model. Look at the results. Concentrate only on the beta hat. All right. So where is the beta hat? So the beta hat is over here. 0.15. What does this mean? It means that if sales increase by $1 million, CEO salaries increase by $0.015,000, which is to say CEO salary increases by 0.015 into 1,000, $15. Okay, that is what this result is saying. Okay, all right. Now, let me see if L salary is already defined. So, yes. So you see there is already a variable called L salary. So this is natural log of salary. All right. And L sales is natural log of sales. These variables are already there. And as you can see, salary is in $1,000. It is a CEO salary in 1990. And sales is in millions of dollars. It is firm sales in 1990. This is the data. And I just ran a level model. And the basic message here is when you have a level model, all you need to interpret is just apply the units in which the variables are measured. Nothing else is really that important. Okay, you don't have to do anything much more to it than that. You just take this 0.0154 thing, and I multiplied it by 1,000 because CEO salary is measured in 1,000. to say that $1 million increase in sales will increase the salaries by 15%, $15. So if you want to say $100 million increase, and you multiply 15 by 100, and you say that $100 million increase in sales will increase the CEO's salaries by 1,500. Okay, right. So that is what. Now let me run a log model. So I will now regress. I will regress log of salary on log of sales. Both are in log form. Now look at my explanatory look at my beta hat. As I said, focus on beta hat, right? What is this? This is 0.25. Now remember, log model, there is no need to do any multiplication or anything of that sort. So what will you now do? You will just say that a 1% increase in sales is associated with a 0.25% increase in CEO salary. The beta hat itself is a percentage in a log model. Okay, so repeat, 1% increase in sales, because sales is in log form, leads to a 0.25% increase in CEO salaries. That's how you interpret the result from this model. Okay, right. Now let's take a semi-log model. So let me regress salary on log of salary on sales. Okay. So what kind of a model is this? This is dependent variable in log, but explanatory variable is in level form. Okay. So I'm regressing log of salary on sales. Now, what do you have to do now? You have to multiply the beta by 100. Once you multiply the beta by 100, then you get a percentage effect. So let us do that. Okay. So yeah, this is that 0.00 thing, right? Yeah. So you will take that 0.00 thing. How many? 4. 0.00015 into 100, right? And what will you get? So 0.0015%, right? So a unit change, $1 million sales increase will lead to 0.0015% increase in CEO salaries. So $100 million increase in sales will multiply this with another 100. So I will get a 0.15% increase in CEO salaries with a $100 million increase in sales. Basic thumb rule: model is a dependent variable in log. This is in level. Take your beta hat, multiply the beta hat by 100, and that is going to give you a percentage change in y associated with the unit change in x. Okay. So this is one kind of a what do you call it? This is one sort of semi-log model where dependent variable is in log form. Now, suppose it is the other way. Suppose that my dependent variable is in level form, but this is in log form, right? So now this is a semi-log model where this is in levels, but this is in log. Now what do? Now I take this and I divide it by 100. Right? So this is my beta hat. So what you do is you take your beta hat, right? And then you divide this by 100 so that you get 2.62%, right? 2.63. If you round it up, it's 2.63%. What is this 2.60%? It tells you that, sorry, it's not a percent. Okay, it's not a percent. So you get 2.63. So what is this 2.63? Why isn't it a percent? It's not a percent because, you know, salary is in level form. So this is for a 1% increase in sales, because sales is in log form. CEO's salary will increase by $2,630,000. So $2,630,000 is $2,630, right? So when you have a model with dependent variable in level but explanatory variable in log form, you take the estimated coefficient beta hat, you divide it by 100, which is exactly what we did. We divided this by 100, right? And then what we got was this, and then we multiplied it by 1,000 because CEO salaries is measured in 1,000. So I hope that, one more thing that you are getting from all of this discussion that we are having is that the units, okay? Again, especially this is a message for my dear research scholars. You tend to forget about that altogether, but it is of paramount importance when it comes to interpreting your results. So when you are, running a model, always interpret your results keeping in mind the units in which you have measured your variables, the dependent variable and the explanatory variables. Because, I'll give you an example. I will just give you an example of what I mean. So here, the example that I have just talked about, my salary was in $1,000 and sales was in logarithmic form. Then I have shown you some other examples. In particular, let me take you back to this particular example where, where salary has been regressed on sales. So what am I talking about now? I'm now talking about the importance of the units in which you measure variables, the importance of keeping that in your mind. You see, when I regress salary on sales, how do I interpret the coefficient? It is 1 unit change in sales, $1 million increase in sales associated with 0.154,000 increase in salary, right? Now, suppose I were to run a model with a different variable. Suppose I were to regress salary on return on equity. Sorry. It's giving me an error message because I made a mistake. Okay, so so suppose I regress salary on returns on equity. Now remember, what is returns on equity? So return on equity is actually measured as a percentage. It is average return on equity of the CEO's firm. This is measured as a percentage. So then, suppose that I have that. Earlier I had sales that was measured in millions of dollars. But suppose I have return on equity, which is a percentage, and I get this result. How do I interpret that? This is going to tell me if ROE increases by 1 unit. What is 1 unit? 1 percentage point. Okay? Because ROE itself is a percentage. So if ROE increases by 1 percentage point, the CEO's salary will increase by $18,500. So again, my research scholars, my message to you is that, when you're interpreting results, be very careful. Be very careful to note what are the units in which your variables are measured, so that, you are not making mistakes and you're interpreting the results very correctly. Okay, all right. So this is something that I wanted to discuss, and it is now taken us through much of the first topic that I wanted to discuss, which is how do you look at certain types of nonlinearities in your ordinary least squares framework in the form of log-log and semi-log models. We have looked at the interpretation in terms of theory. We have run the results, and we have also interpreted the results with some real-time data. So I can see questions are piling up, but I will take questions at the end of the session. So let me finish what I had in mind for a little bit more, and then I'll collect and I'll try and answer as many of the questions as I can. Okay. Now, let us move from this particular non-linearities based discussion to the more general multiple regression model. Let me actually begin by running a multiple regression model right here. So I will now regress CEO salaries on sales as well as returns on equity. Now, yesterday I got some questions on what is a multiple regression model in terms of dependent variable and explanatory variables. So you see, we are looking at a multiple regression model or a three variable model. What are the three variables? One dependent variable. So throughout my discussion, I'm going to be discussing models where the dependent variable is always one, single dependent variable. So where I have one dependent variable, but now I have two explanatory variables. There is ROE, which is measured in percentage points. It's the return on equity of the firms. So this is a cross-section data. It's a cross-section data on CEO salaries, and for each of the firms for which the CEO salaries are being reported, you have the firm's return on equity for the past 3 years and the firm's sales in that year, the year in which the salary is being given. So when you do that, you are looking at a model where y is equal to alpha plus beta 1 x1 plus beta 2 x2 plus u. Okay, that's the theoretical model. And now, what are you getting out of this model? Well, so let me just maybe write the model briefly. So my model is y is equal to alpha plus beta 1 x1. So alpha is, mind you, the alpha is the intercept term. Okay, it is the, yeah, beta 1 x2 plus u. So you see, now I have two variables. So it's no longer a straight line. It's now becoming a plane. So I can't draw a picture and all that, but you know, the linearity means that you know, all the model is still linear in parameters. The error term has the same interpretation. It is an unobservable random variables. We assume that the errors are homoscedastic, that they are independent, and so on. Okay, there's an extra assumption which we throw in a multiple regression model, which is that x1 and x2 cannot have perfect correlation. You know what is perfect correlation, right? When the correlation is either exactly 1 or -1. That case has to be ruled out as an assumption for our linear multiple regression model. Now, in this case, I know that there is imperfect correlation. How? Because the model is being estimated. If there was perfect correlation between x1 and x2, then the model would not even be estimated. I will show you this in the afternoon today when I talk about something called the dummy variable trap. So we'll fall into that trap and then we will see what it feels like. Okay? Right. So now to come back to what we are doing, we are estimating this sort of a multiple regression model where y is CEO salary, and I have two explanatory variables, return on equity and sales, corresponding to which I have beta 1 hat and I have beta 2 hat. Now, it's good to note that both of the variables are statistically significant. How do I know that? I know that by looking at the p-values. Now, what is the thumb rule in case of p-values? The p-values, if the p-values are very small, then we reject the null hypothesis that beta 1 is equal to 0 and beta 2 is equal to 0. Separately, we reject these two null hypotheses. Now, some of you may be wondering why she's saying that null is getting rejected, p-value is greater than 0.05. ठीक है, p-value is greater than 0.05, but it is less than 10%, no? So that's fine. in our classical linear regression analysis, we can reject nulls either at 1% or at 5% or at 10%. Okay. So there is nothing like that. 5% is like fixed or something like that. So clearly at the 10% level, I'm rejecting both the nulls, beta 1 equal to 0 as well as beta 2 equal to 0. So in case there are questions on p-values, etc., I will take it up during the question time, answering time. All right. So right now I'm just noting this. Now, let us see how we interpret this. What changes? Something very important changes when you are interpreting your results in a two-variable model or in a multiple regression model compared to a simple model. So what changes is now these become partial derivatives. So now your beta 1 is actually equal to del y del x1. Your beta 2 is now equal to del y del x2. What does that mean? It means ceteris paribus. Okay. Ceteris paribus literally means holding other things constant. So that is the most important thing I want you to remember when you are interpreting a result from a multiple regression model of the kind that we have just estimated. So in this model, I will say that holding sales constant, if ROE increases by 1 percentage point, the CEO's salary will increase by $19.6 thousand. I repeat, I will interpret beta 1 hat in the following way. Beta 1 hat is telling me holding sales constant, if ROE increases by 1 percentage point, then the CEO's salary will increase by $19.6 thousand. Everything in this model is measured in terms of levels. There are no log, there is nothing, there's no complication. So straight, I will just interpret the results in terms of the units in which these variables are measured. So if I were to instead look at, if I were to instead look at beta 2, all right. So if I were to look at this, what is this saying? This is saying holding sales constant, okay? If I were to increase, holding ROE constant, if I were to increase sales by $1 million, then CEO salary would be increasing by $0.016 thousand dollars. So clearly, you can see that sales and ROE, each of these things have a slightly different impact on marginal change in CEOs' salaries. Okay. Now, let me hold forth a little bit more on this ceteris paribus bit. What does it mean actually to hold things constant? Okay. So what does it mean to say ceteris paribus? Let me just say that. You see, multiple regression is a very powerful tool. What is it telling you? It's telling you that, look, if you have two firms with exactly the same amount of sales, but one has a higher ROE than the other by just 1 percentage point, then that firm, the one with the higher ROE, is going to pay its CEOs $19.6 thousand more. Let me repeat. What does it mean to hold sales constant? It means you're saying, suppose I have two firms with exactly the same sales. The one with higher ROE, how much higher? 1 percentage point higher, will pay its CEOs more. How much more? $19.6 thousand more. Do you see? Let us interpret the coefficient of sales in the same way. Holding ROE constant, if sales increase by $1 million, CEO salaries increase by $0.016,000. What does that mean? It means if you have two firms with exactly same ROE, that's what it means to say holding ROE constant. If you have two firms with exactly the same ROE, the one which is selling 1 million and the one which is selling $1 million more will pay its CEO $0.016,000 more. So you see why I am telling you multiple regression is such a powerful tool. You don't need this in the data. You don't need to have actual data on two firms with exactly same ROE and exactly same sales. There can be, maybe, I'll see that there are no firms which have exactly same sales. There are no firms with exactly same ROE. That can happen. So irrespective of the data, multiple regression is allowing you to estimate this very important ceteris paribus effect. Now, this is especially for researchers. My dear researchers, please, exploit this power of multiple regression. Every time that you are running a multiple regression model, you're saying this, except that you're not really saying this. You're just, I've seen many young research students who, when they get started, get lost into this alpha hat and beta hat and bus. Get out of that alpha hat and beta hat, whatever, and look at the units in which your variables are measured and talk about your results. Talk about it in the form that you can talk about them, right? Okay. Exploit the ceteris paribus power of multiple regression. So I will just take you through the assumption of the multiple regression model and then I'll take questions. The remaining topics I will take up after the break because I realize that it is now 11:30. Okay, so yeah, okay. So I will just show you the assumptions of the multiple regression model. So I had talked about the assumption of the two-variable model, and multiple linear regression model can be easily generalized. So the two-variable model can be easily generalized into the multiple linear regression model. So you have the same linear deterministic relation between the average value of y and the explanatory variables. The model is linear in parameters, so that this is our model. And the original model, of course, would have an error term in it. So y is equal to alpha plus beta 1 x1 plus beta 2 x2, etc. plus u. Okay. Now, remember, most of our assumptions are about the random error terms. They remain the same. These are zero mean. They are constant variance or homoscedastic. They are independently distributed. Zero correlation between the error terms. None of the x variables must be a constant. Okay. Now, what is the new assumption? The new assumption is right here in red. By assumption, we are ruling out perfect correlation among the x's. Now, this is rarely observed, so not something to worry about, but something to definitely note. This is known as the assumption of no perfect collinearity. So no perfect collinearity literally means that I am assuming that my explanatory variables do not have a correlation of either 1 or -1 among themselves. Okay, so now comes to the correlation between your explanatory variables and the errors. Right? So first was your assumption. So first is the correlation among the explanatory variables themselves. There, all we are saying is no perfect correlation. What does that mean? It means don't lose sleep if the x's are correlated. ठीक है भाई, correlated है, रहने दो. Nothing, there is no harm in that whatsoever. So far as the assumptions of your model is concerned, don't lose sleep. Okay. As long as it is not perfect, which it rarely is, there is nothing wrong in your model assumptions if the X's have correlation. Obviously, return on equity and sales have correlation. So, hone do, big deal, I don't care. Model assumptions are fine. Okay, please keep that in mind. So that is the first thing about the assumption. And the second assumption is about the assumption of the X's and the errors. There we have to say that they are uncorrelated. Okay. We also assume that in our two variable model. And finally, we assume that the errors are normally distributed. Okay. Right. So these are the assumptions, and as I said that how do you actually interpret the slope coefficients? Each of these slope coefficients in your multiple regression model is measuring the change in y associated with a change in x holding all other x variables constant, which we just discussed. So of paramount importance regarding the interpretation of coefficients in your multiple regression model is that you are holding all other x variables in the model. So please see, I have also put in the model. You're only holding constant those variables which you are putting in the model. Bas, okay? Holding those constant, what is the effect of x on y is what is being captured by the estimated coefficients. Okay. Bas. I will end this session here, and now I will take questions. So I will look at the chat now, and I will try and see how many questions I can answer. So, I will go up. So I will look, because I'm assuming some of the questions earlier may have been answered during the session. So I will take the ending questions and then I'll climb up. Okay. Okay, so it's good to see some of the, so Sagar, I see you. And then I see Saranya, I think I saw you guys yesterday as well. Saida, hello, how are you? Online classes are very nice, but I really miss not seeing all of you. Yeah. Pooja, when to use log-log and semi-log model? Pooja, that's a very difficult question. It depends on the context. Mostly trial and error. So Pooja, sometimes the theory will tell you. So if you are an economics student, then you must have heard about the Cobb-Douglas reduction function. Now, if you want to estimate the Cobb-Douglas reduction function, you have to use a log-log specification. Why? Because when you turn that nonlinear production function into a linear model by taking logs, you will see you'll have to regress log of output on log of labor and log of capital. So here there is no option of semi-log. It has to be log-log. So sometimes the answer to Pooja's question comes from the theory. The theoretical specification itself tells you whether you should use log-log or semi-log. But sometimes it is not like that. Let me take the CEO salary. Should I regress CEO salary on sales, or should I regress log of CEO salary on sales? How do I answer that question? That question is not that easy to answer actually. And I will actually opt for log of CEO salaries on sales, because it will give me a constant percentage effect. But then who's to say that there are no diminishing returns? Shouldn't I try out salary on log sales? Why not? So the question is really trial and error when you don't know any theoretical, when there's no hard theoretical algebraic model that is guiding your regression. Okay, so really that is the way. If I can think of any other answer to your question, I'll come back to it. Sangeeta, why is multiple regression better than simple linear regression? Yeah, okay, great. That's a very good question. It is much better because you see, suppose, okay, yeah, I love your question, Sangeeta. That's because I have seen my students do the following thing. They will come and tell me that, ma'am, I want to look at the relation between CEO's salary and sales. But I don't want to look at anything else. So I just ran a regression of CEO salaries on sales, and here are my results. So you see, that might be a way of looking at things, that I am interested in the relation between Y and X, but nothing else. So I will just regress Y on X, end of story, go home. No, 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 it is not that simple. You may be interested in the effect of Y on X, all right? But in reality, Y may be a function of X1, X2, X3, X4, X5, X6, X7. You cannot be an ostrich. You cannot shut your eyes to that, right? So let me actually explain why not. So you see, what I'm saying is that, suppose in reality, Y is a function of X1 and X2. So this is your true model. Beta 1 X1 plus beta 2 X2 plus U. This is actually the case. Okay, this is the true model. But you are doing what? You are just regressing Y on X1 because you're not interested in X2. Now the errors from this model, mind you, is new. It is not you. So this is what you are doing. Okay. Now look at what is happening. What you think is the error is actually not the error. Why? Because you think, हाँ ठीक है, ये error है, random है. अरे भैया, इसमें बैठा है beta 2 x2 plus u. This is the error. So do you understand what happens if the correlation between x1 and x2 is not equal to 0? Then what is happening? Do you see what is happening? If the correlation between x1 and x2 is not equal to 0, then what will happen is that your x1 and mu will get correlated. So this model is basically going to violate the assumption of zero correlation between x and errors. So let me repeat. Suppose in reality, y is a function of x1 and x2, this model here. But for whatever reason, you are ignoring this multiple regression model, you're ignoring model number 1, and you are estimating model number 2, where you're running a simple regression model. Then you are committing a grave error. In your model, coefficients will be biased, because in your model, what you think is the error is actually not the error. It is actually beta 2 x2 plus u. And if there is correlation between x1 and x2, then in your model, in model 2, the errors will get correlated with the explanatory variables, violating the assumptions of our two variable regression model, violating the assumptions of our regression model. So do you see that is going to be something pretty problematic. So you may be interested in only one thing, but don't let that make you run a two variable regression if in reality y is a function of many things. You should be controlling for those many things. When we put things into the model, when we put variables into our model, we say we are controlling for them. Then you can say that, you know, controlling for all these other x's and so on, okay, controlling for all these x's, you can say that you can say that you know, the effect of what is the effect of x on y, okay, x on y. So I hope that this answers the question. What is a huge advantage of multiple regression over simple regression? Simple regression has no controls. All right. Now here, just let me make one more point, which is that you see. Uh, Suppose you so let me stay with this example. Okay, so let me stay with this example that this is the model I have estimated. I've estimated model 1 where I've regressed y on x1 as well as on x2. Okay, and I find that x2 is insignificant and I find that x1 is significant. So remember, that is all you care for. That is all you care for. So you still have good results if what you are interested in is significant and has the correct sign. So the fact that you put this in, you put in x2 because actually y is a function of x2 and there is non-zero correlation between x1 and x2. Therefore you put it in and it turns out to be insignificant. Koi baat nahi, rehne do, let it be. You're controlling for x2 and you're getting a result on x1 and you're getting rid of bias in your results. Okay, right. So, okay, so I think the questions are here. Let me get back to the questions. Yeah, well, okay. So there are many questions. I'm not sure. Should I continue or should we take a break? Yeah. Should I? Okay, so I'll wait for someone from Ramanujan College to actually interrupt us. Till then, let me continue. I'll take your questions. Okay. All right. So, which confidence interval would be best? Again, there is no such best. Look at everything, but realize if you choose, there's a trade-off between accuracy and what should I say? So as you change your confidence limit, the width of the interval changes. Okay. So if you say 99% confidence interval, all right, then that is 99% probability, very high probability, but then the confidence interval is also that much wider. So if you go for 90%, there's a 10% chance of being wrong, but then the confidence interval is smaller. So the width of your interval varies as you change the confidence limits. Okay, so 95 is therefore middle of the road. There's a 5% chance of error, but then the interval is not as wide as 99, nor is it as small as 90. It's kind of in the middle. So those are the principles. So one message to all of you, research is all about trial and error and learning and relearning. I mean, believe me, since I started on Monday, I have learned so many things while going over all these, basics with you. So, I mean, there isn't someone sitting out there who knows everything and will tell you, "Acha, aisa ho raha hai, aise karo." It is not like that. It is always, it's a bit like swimming. Research is a bit like swimming. You kind of, you haath pair maro and then you learn, right? And then before you know anything, you are teaching the next one. So it's a bit like that. So nobody has the answers, right? Even Nobel laureates are learning. Okay, so I think keep that as a kind of thing. Okay.
Thank you, ma'am, for your suggestion and the comments. Ma'am, can we have some questions now so that the second session is not delayed? We can have it for 5 minutes if that is okay, ma'am.
Yeah. So I'm just answering the questions.
Ma'am, you want me to read it out or you'll just scroll it through the Q&A?
I'm seeing the questions and I'm answering them. So
Ji,
now I'm going to Sonia's question. Interpretation, whether our CEO salary is following all the assumptions. Sonia, I don't want to take your question right now. Whether it's following the assumptions is not something you can say by looking at the results. You'll have to look at the residuals. Okay, so I will not answer your question now. Once I've looked at multicollinearity, etc., at the end of today's session, you'll get an answer to your question. That once I have some results, are they actually obeying all the assumptions? Okay. All right. Now, Dr. Reeti Gaur, what's the difference between error and residual? Reeti, we discussed this yesterday at great length. So error is unobserved. It's a theoretical part of your model. So U is your error. And residuals are what you get after you have run your model. So the residuals are U hat. So you calculate your residuals by taking the difference between Y and Y hat. So if you refer to the Excel file, which will ultimately be shared with you, you have calculated the residuals. So the errors are random variables which are unseen, but residuals are very much to be calculated and can be observed. Okay, that's the difference. Heteroscedasticity, Renu Verma, I'll come back to heteroscedasticity. Difference between MLR and partial MLR. I'm sorry, Shima, I don't know what is partial MLR, okay? So I don't have an answer to your question. In your model, Nilotpal, your model, the dependent variable ranges from 0 to 1. What model should I use? Yeah, okay. I don't know, is it... you can use a multiple regression model, okay? That there isn't anything like that, but I don't know whether it's a dependent variable. Is it only taking binary values, 0, 1? If it is taking just 0, 1 values, you can still use multiple regression, but it is also advisable to use a logit model, which you'll be looking at later. But if it takes all kinds of values in a 0, 1 range, you can use multiple regression. There's nothing really wrong with that. So that is, if it has a lot of zeros, to it can be a sort of a way out. All right. Shanti is asking, Dr. Shanti is asking how to decide at what level of significance. Okay. So Shanti, you're guided by the p-values. The p-values are telling you the exact level of significance at which your hypotheses are getting rejected. Okay. So typically we start with 1%. We move to 5% and then we go to 10%. We normally don't cross 10%. So if something is getting rejected up to the 10% level, we take it as a rejection of the null. Okay. How do you test for data stationarity? Zabiullah, Dr. Zabiullah, I'm not answering that at all because this is not a session on time series. So if you say have a session on time series in the program, then you will learn about stationarity. In a cross-section data, we never test for stationarity. The concept does not arise at all. Okay. Example, yes, Megha, I will do an example of a quadratic variable. I will do that. Level log is also to be used for explaining diminishing returns. Level log, yes, yes. Rakhi Saxena, yes. We use a level log model to explain diminishing returns. Anonymous, are you teaching only economic students? I don't know who I'm teaching, my dear. So of course there could be a mix of students, but my failing, or I wouldn't say failing, my standing is on economics. I am a student of economics, so therefore that is the limit of my knowledge. So do pardon me if there's too much of economics, but that is my bread and butter. So perhaps I can't escape that. Kaustav Roy, you can certainly use XXX. So I think Kaustav, you're suggesting a kind of a model with an interaction term. Now I have seen models with interactions, a single interaction, but you are saying model with beta 1x plus beta 2x squared plus beta 3x cube. You can do that. Yeah, you can do that. Why not? Only be careful about how you are interpreting the results. There's nothing that prevents you from running a model with, x raised to the power 3 as a explanatory variable. Okay, yeah, that's fine. Level log to be used to explain diminishing returns. Why chat is disabled? Yeah. Saida is saying that multiple regression results p-values was 0.07 and 0.06. Yes, Saida, they're significant at 10%. They're not significant at 5%. Yes, but then 10% is also allowed. So at the 10% level of significance, I'm rejecting the null that beta is equal to 0 with these p-values of 0.07 and 0.06. In fact, you don't even have to go up to 10%. So one is getting rejected at 6% and one is getting rejected at 7%. So that's fine. All right. How do I decide, Ankita? I hope I've answered my question. There is really trial and error. If you have a theory, great. If you don't, you have to run. I'm quoting one of my PhD students. She actually, at the end of her thesis, with a smile on her face, kudos to her, told me, "Ma'am, I almost ran 1 million regressions." So it's like that, okay? So I mean, I'm very fond of that student of mine because of the way she kept at it, running 1 million regressions over 5 years, but that's still a lot of work. So that's how you decide. You just find out what's best. So it's best to grab on to some theory. If you have the theory, then the functional form is there for you. Okay, right. I think, I think that answers most of the questions, so far as I can see. So,
Okay. Thank you,
yeah.
ma'am. Thank you
Thank
for
you.
answering or taking up almost all the queries. We break for we have a break now, ma'am. We'll just meet at 12:10, ma'am, because we have delayed this session. So we'll come back by 12:10. Okay.
We'll do that.
Thank you.
Okay.
Thank you.
Bye. Bye.
The participants are requested not to log out from the webinar. The next session will be on the same link in case you log out. Thank you.
Thank you, Amir. Okay.
morning, Amir. Or maybe it's my internet. Can you hear me?
Ma'am,
Your voice is
yes,
breaking,
ma'am,
ma'am.
you are clear. Yes, ma'am, you are.
Okay, so can I start?
Yes, ma'am.
Okay, so
Yes,
I'll
ma'am, now it is
start.
clear.
Amir,
Now it is all.
I can't hear you very clearly. It's breaking a bit. Okay,
Okay, ma'am,
so
you can start.
I'll begin. Okay, so we are now talking about as we had planned. We have introduced the multiple regression model. We have uh, talked about non-linearities. I'll come back to models with quadratic terms. Allow me to cover a bit of ground so far as some of the other topics I had in mind, and then I'll come back to estimating a model with quadratic terms. Okay. So I wanted to talk about a problem of multicollinearity, which is frequently discussed in the context of multiple linear regression models. So let's start with what is this problem of multicollinearity. Now, multicollinearity is actually a part of the data generating process. All right. So the thing with multicollinearity is that we have to just live with it. Okay, we have to live with multicollinearity, which involves the extent of correlation among the explanatory variables themselves. So please keep this in mind that uh, when the explanatory variables are correlated with each other, and there is a high degree of linear correlation among the explanatory variables, we say that there is a problem of multicollinearity. Okay. Now, let me first of all set the record straight, distinguishing multicollinearity from perfect collinearity. Okay. Now, what is perfect collinearity? Perfect collinearity is actually something that is ruled out via assumption. We just said that, right? We said that the explanatory variables should not have correlation of 1 or -1. Now, why is that? We will shortly look at something called an X matrix to understand why that is the case. Why do we have to rule out perfect collinearity? Now, having distinguished between multicollinearity, which is correlation but not perfect correlation, and so between multicollinearity and perfect collinearity, which is correlation of 1 or -1, let us see that while perfect collinearity is a huge problem, so much so that it has to be ruled out by assumption, multicollinearity is really not a problem in the sense it does not violate any model assumption. None of our model assumptions are ruling out existence of correlation among the explanatory variables. What is being ruled out is the correlation between the x's and the errors. That has to be ruled out. But the x's can be correlated. Our model is silent on that. Only perfect correlation is ruled out. So therefore, you might wonder, then why are we even talking about this? What's the problem? Okay, that's really part of the deal. What is the problem? Let's try and understand that. Now here, once again, let me reiterate that there's nothing we can do about multicollinearity because often it's part of our data generating process. So ROE and sales, education and experience, I can often have them in models together as explanatory variables, and they're related to each other. What can I do about it? Nothing. That's the way that data gets generated. That is the way the labor market works. People with more education have more experience, and so we tend to have a high correlation between education and experience. I can't do anything about it. Okay. Similarly, firms that are doing very well in terms of sales, who are the market leaders, may often offer higher returns on equity. There's nothing I can do about it. So basically, my two very important messages from this slide. Number one, given what is multicollinearity, we have to live with it. And second, that's not so bad because it does not violate any model assumption. Okay, at the outset, let me make that clear. So then, what is the problem if the model has multicollinearity? So all the hard work we put in yesterday in looking at the variance of the estimators, the answer lies over there. Why is multicollinearity a problem at all? Okay, so let us look at that. Okay, so first, yeah, I'm now talking about my notes. The first thing is that okay. The first thing is that OLS estimators are blue even in the presence of multicollinearity, as long as we have ruled out perfect multicollinearity, right? That's the first point. Now, why multicollinearity is a problem? Look at the variance of your beta hat j in a multiple linear regression model. So what is my model? My model is y is equal to alpha plus beta 1 x1 plus beta 2 x2, right? And so on. So I assume, sorry, so this is x1, beta 2 x2 plus, so I assume that I have k explanatory variables, all right, plus beta k xk. This is my model. So where the betas are all unknown parameters. Now I have a multiple regression model. I have k plus 1 unknown parameters, k slope terms and alpha, one intercept term. K plus 1 unknown parameters are going to be estimated. And the OLS estimators are, remember, they have hats. So beta hat is the estimator for the jth. So this beta hat j is the estimate, is referring to the jth beta. Okay. Now remember, the beta hats are all random variables. So each of these, so once I've run my OLS model, my beta hats are all random variables, which is why they all have means and variances. Under the assumption they are unbiased, and if there's multicollinearity, there's no problem of bias. So variances are all, the estimators are all unbiased, even if there is multicollinearity, as long as it's not perfect. Okay. So in the presence of multicollinearity, the estimators, as I said, are blue. So so they are unbiased. And so as I said, where is the problem? Look at the expression for the variance of beta hat j. In a multiple regression model, the variance of beta hat j is a function of sigma square. It was also a function of sigma square earlier, yesterday, when we looked at variance of beta hat in the two variable model. Now it's a function of the total sample variation in the x variable. So if I'm talking about beta 1, I'm saying the variance of beta 1, the variance of beta hat 1 is a function of sigma square. It is a function of the total variation in x1. If I'm talking about beta hat 2, the variance of beta hat 2 is a function of sigma square, and it's a function of the total variation in x2, and so on. So the variance of beta hat j is a function of total variation in xj. That is this term. Now what else is it a function of? Now there is a new expression over here, which was not there in the two variable model. So in the two variable model, we didn't even talk about multicollinearity. But now, with more than one variable, the question of how they are related to each other, correlated with each other, comes up. And why that correlation can be a problem is lying right here in the expression of the variance of beta hat j. So look at this term here. Look at this term r squared j. Okay. So what is this r squared j? R squared j is an r squared from a regression where I'm regressing xj on all the other explanatory variables. I'm not running such a regression, but I can run such a regression. Okay. And you have to run such a regression when you are calculating the variance of beta hat G. So your package is doing it. When the package is reporting standard errors, it's actually running all this regression in the background, and then it is giving you the standard error. So please understand this. What do I have? I have a multiple regression model, which means I have many explanatory variables, x1, x2, up to xk. Now, there is a correlation among these variables, and I have multicollinearity. Where does that matter? It matters right here in the standard error, okay, of the estimated slope coefficients. Why does it matter? Because as you can see from the expression of the estimated slope coefficients, so I will delete all of this. So carefully look at the expression for the estimated slope coefficients, okay? So what do you see? In the numerator, there is sigma square. What is sigma square? It is the error variance. Okay. Denominator, there is a total variance of the x term. So if I'm talking about beta hat 1, the denominator has total variance in x1. If I'm talking about beta hat 2, denominator has total variance of x2. That is one term. And what is this term? This is where multicollinearity comes. If there is high correlation among the x variables, then this R squared value will be very high. Then when I run a regression of one explanatory variable on all the others, and if they are very highly correlated, I'll get a very high goodness of fit. Now what will that do? That very high goodness of fit will reduce this term. If R squared j is very high, then 1 minus R squared j will be very low. And if that is the case, what will happen to the variance of my estimators? The variance of my estimators will be very high. Okay. Now, if variance of my estimators is very high, then what is going to happen? The standard error of beta hat j will be very, very high. Now, if the standard error of beta hat j is very, very high, what will that affect? It will affect your t statistics. Remember, yesterday we said that the t statistic is nothing but beta hat j upon the standard error of beta hat j. So now begin to appreciate why multicollinearity is a problem. It is a problem because it inflates the variance of our estimators, which in turn inflates the standard error of the estimators, which in turn tends to lower the statistics. So standard error is in the denominator of the t statistic, right? So this is equal to my t statistic. So for any given beta hat j, if you have very high multicollinearity, you're going to have very high standard errors. And those very high standard errors sitting in the denominator of your t-stats are going to lower your t-stats. Now remember your t distribution which we saw yesterday. The t distribution is mean 0. If you have very low t-stats, where are they going to be? They're going to be close to the middle of the distribution. So think about your hypothesis tests. All the variables will become insignificant. Why? Because our variables are significant when the t values are large. Large t values lie in the tail of the distribution. But what is multicollinearity sitting there and doing? It is driving down your standard errors, and it is therefore, it is driving up your standard errors, it is driving down your t-statistic, and it's pushing the t-statistics in the area of non-rejection. So you see, multicollinearity is not a problem, but multicollinearity is a huge problem at the same time. Let us just see what we are saying. We are saying that, look, multicollinearity is part of the data generating process. There's nothing I can do about it. And why should I even want to do something about it? Because my estimators are blue. So why should I worry about multicollinearity? But you see, in practice, it can be one of the biggest problems that we face as researchers. Because with multicollinearity, you get this phenomena that all the variables which should be significant are insignificant because the standard errors are so high. Right. Now, what do I do about this? Well, there is unfortunately again no simple solution. There is no simple solution. Let nobody fool you on this. Okay. Now, you see, what is happening is that, yeah. So what is happening here is, yeah. Okay, so while I'm sort of on the topic of multicollinearity, let me just tell you that very often we talk about something called the variance inflation factor. Now, the variance inflation factor. So just let me take you back to this. So appreciate where multicollinearity is actually coming in. Multicollinearity is actually coming in the variance of our estimators, right? So having said that, look at a very sort of standard, quote unquote, way of detecting multicollinearity. Okay, this is called the variance inflation factor. Okay, this is called the variance inflation factor. And look at what it is. It is nothing but 1 upon 1 minus r squared j. So the variance inflation factor is in fact just looking at this bit to see to what extent presence of that variable is actually causing some sort of a problem in your regression, in the sense to what extent the errors are getting inflated. The standard errors, the variance of your estimators, the standard errors, to what extent are they getting inflated owing to this high correlation among the explanatory variables. Now remember, we have ruled out perfect multicollinearity, so clearly r squared j cannot be 1. It can be very high. Now if it is very, very high, then what is it? Say 0.99, it is 0.9 or something. So that this thing, if the denominator r squared j is like 0.99, this turns out to be, you know, in the denominator you have 1 by, let's say, 0.0. So that, you know, 0.01 or something. So that, you know, a general cutoff value is 10. So you kind of say that, look, I will look at the variance inflation factors of each of my variables to see which one is the culprit, due to which variable the variance is actually getting inflated. That's all. So so really, the variance inflation factor just tells you to what extent the standard error of that variable is high due to its correlation with the others. Beyond that, you know, the variance inflation factor has no real other sort of implication. Okay, it's just telling you that to what extent the sort of variances are inflated. Okay. So having said all of this, what can we do about multicollinearity? Remember, I just told you that there's no easy fix, and the solution actually lies right here, lies at the problem. So the problem is that it's inflating the variances of your estimators, and the solution lies right there. How can I bring down the variance of my estimators? If this were a live session, I'd ask you, what can I do to bring down the variances? I think many of you would have the answer. I can actually increase this. I can increase the variation in my x, right? And that's exactly the route that economists have taken. So here, I must tell you that if you are a research student in economics, again, my apologies if, I'm talking too much about economics, but unfortunately, well, I won't say unfortunately, but that is my training and that is what I'm qualified to speak on. I'm not really qualified to speak on many other areas. So, so far as my familiarity with the economics research process goes, this is something that the economists have stopped worrying about. I don't remember the last time that I looked at a research paper in a good journal which was worrying about multicollinearity until and unless it created a problem. So how do economists try and beat this this problem? They try to have large data sets. It's as simple as that. So now of course everyone's talking about big data. Big data is like, you need servers to store big data. So you can imagine what kind of variation you're going to see in your X variables if you're actually using some big data for your analysis. So mostly a good way to try and beat multicollinearity is within the constraints that you are working under, try to maximize your data set. Okay. Now, I understand if you're a time series person, that is very difficult. I mean, what can you do, right? So one way out is, if you're working with finance data, you will see that people will work with data coming out by the nanosecond, data coming out by the second, by the minute. All of it serves to increase the variation in your data set. So if you have such large data sets, multicollinearity may not be a problem at all, right? Because for any amount of correlation, suppose your R squared is very high, but if your SSTX chief, if the variation in the X variable is so large, then anyway your standard errors will be coming down, okay? So this is what to do in case you have multicollinearity. Now what not to do when you have multicollinearity, let's also talk about that very briefly. So as I said, if you want to beat multicollinearity, try and have large data sets which ensure very high variance in your X variables. Now, here is a word for those of you who are thinking of primary research. Do you see, if you're ultimately going to run some regressions using that primary research, A, make sure you have a random sample. B, make sure you are trying to use very large data sets. So if you can't do that, suppose you're constrained that, I can't run a very large sample. I have only very small. Then, please think of using large data sets that are already available, like the NSSO. Like the ASI. ASI if you're thinking of doing research with firms, NSSO if you're thinking of households. These are extremely large samples where you'll have a lot of variation. So, those kind of will display sufficient variation in X variables to stop you from worrying about multicollinearity. Okay, that's one suggestion if you are thinking along those lines. Now, sometimes taking log actually helps because, once you're taking log of a variable, and remember natural logs. So then from X, you're suddenly expressing Y, you're suddenly expressing it as to what power I raise E to get this variable. You're really scaling down the variable, and that scales down the variance and just takes care of the problem. So these are some of the sort of first-hand, what I have read. These are some of the ways that I have encountered to sort of handle multicollinearity, right? I'm not an expert on multicollinearity. I really don't have much more to offer on multicollinearity than this, okay? I already discussed using multicollinearity, how you can detect it using a VIF, right? But remember, VIF is as I said, it's not like the be all and the end all. All right, so it certainly is telling you something. Realize what it is telling you, but then what you do with that information is really up to you and so on. Okay. Now, as I said, I will be telling you what not to do, right? What not to do when you are facing multicollinearity. Okay. So make sure you do not drop relevant variables in an effort to avoid multicollinearity. So suppose you have a regression of y on x1 and x2. Let's say you have a regression of y on x1, x2 and x3. Okay, and you think that there is multicollinearity. Oh, तो इसको छोड़ो, x3 को निकाल दो. Don't do that. Please don't do that, because that can actually lead to a very serious error, which can actually violate your assumptions, because multicollinearity is actually not violating assumptions. But now if you drop a variable, that can lead to the problem of omitted variables bias, leading to a violation of the assumption of zero correlation between X and the errors. So this is something I discussed just before the break. And I think I'll just quickly, return to that, so that, we can quickly have a look at that. So, right. So if you remember, just before the break, we talked about this particular situation where suppose this is my model, right? Suppose this one is my model, and I think that there is a lot of multicollinearity between x1 and x2, right? So what do? I go and I drop x2, and I just regress y on x1, and I do model 2. But if I do that, and if there is multicollinearity, then certainly the correlation between x1 and x2 is not zero. And then x2 is sitting right there, because this is the true model. So you think that the errors are homoscedastic and the errors are uncorrelated with the x's, but actually the errors are what you think. So you think errors are mu. But actually, what are the errors? The actual errors are u. That is what the original model has shown us. So your assumption that the errors are uncorrelated with the model x1 and nu, right? In model 2, x1 and nu, the correlation is not zero, right? Why is the correlation not zero? The correlation not zero is because x1 and x2 are correlated, and nu is actually beta 2x2, which you have left out of your model, plus u. So the correlation between x1 and u is zero. So x1 and u, these two are uncorrelated, surely. x2 is uncorrelated with u. But if you have dropped a variable to avoid multicollinearity, you are now suffering, your model is suffering from omitted variables bias. Because you see, this particular assumption, if this assumption gets violated, your estimators will not even be unbiased, forget best, right? So unbiased is a basic requirement. They will not be centered at the unknown parameters. It is going to be a very serious problem with your model. So whatever else you do, make sure that you avoid this tendency to drop variables simply to, avoid multicollinearity, okay? Having said that, you may ask me, so then what do I do? Again, I'm really sorry, I don't have answers as to what you do. You have to try out different specification. Maybe a log specification will work. Maybe some other form will work, but you have to think about it. And that's what research is all about. It's not without reason that it's called research. Search, research, right? It's a lot about figuring out what to do, right? Okay. So that's so far as the problem of multicollinearity, which is one of the things that I had wanted to discuss with you. Okay, so I will take you to Stata, and then I will certainly show you how to get VIFs and so on. But before that, let me talk about the X matrix. Now, why do we want to talk about the X matrix? Because you see, we'll have to look at the X matrix to understand why perfect collinearity had to be ruled out, and also to understand something called the dummy variable trap. Because now we can start looking at models with dummy explanatory variables, having discussed this problem of multicollinearity. So to take you back to our talking points, yes. So we looked at nonlinear relations. We'll come back to models with quadratic terms in a little bit. We have looked at interpretation of results in the multiple linear regression model. We looked at assumptions. We'll keep on looking at hypothesis tests. As we carry on, we'll keep discussing hypothesis tests. We looked at the problem of multicollinearity. Here, just let me reiterate that so far as interpretation of results in the multiple linear regression model is concerned, the most important thing is the ceteris paribus, holding other things constant. Okay, right. Now, I want to talk about models with dummy explanatory variables. Let me show you what dummy variables are and what are these models with dummy explanatory variables, and then I'll talk about the X matrix. Okay, the X matrix, which will help us understand the dummy variable trap. It will also help us understand why we rule out the assumption of perfect multicollinearity. Okay. Okay. Now, okay. So now we are looking at some basic concepts regarding dummy variables. Okay. So what are dummy variables? They are what we call binary variables, which take only two values, either 0 or 1. Okay. Now, now just let me pause here and say the following thing. If you have questions on multicollinearity, etc., just note it down, all right? Note it down and I'll come back to questions at the end of the session. I've also not forgotten about Stata. I will show you how to do regressions on Stata, okay? So all of that is coming. Let us walk through some of the theory and then we'll do Stata, okay? Stata questions or everything will happen, all right? Okay. So to talk about dummy variables, I'm going to talk about models which have dummy explanatory variables. So later on in this FTP, you will also find sessions on models, logistic models where you have dependent variables that are explanatory variables, which are dummy variables. I'm not going to talk about those. So I'm just talking about what happens when some of our independent variables are dummies. Now, these dummy variables, they give numeric values 0 or 1 to certain qualitative attributes, such as marital status. So 1 if married, 0 unmarried. Gender, 1 male, 0 female. Educational qualification, 1 if MA, 0 is less than MA. Occupation, 1 if an officer, 0 not an officer. Okay. So you just use dummy variables to clearly demarcate groups in your data. So you have a group of people who are married, you have a group of people who are men, you have a group who are more educated. So dummy variables are just a kind of trick, just a way of numerically picking up those groups. So typically, sometimes nominal variables are used to identify groups in the data. I'll show you what I mean. And then you convert those nominal variables and give them numeric values using dummy variable. So essentially, the use of dummy variables is to help combine different groups into a single large database. That's one good thing. You can put them all together as a single data, and yet you can separate out the parameters for each group. So you can separate out that, this is the regression line for men, this is the regression line for women, this is the one for married people, this is for unmarried, this is for educated, this is for uneducated, etc. Okay. So this is when we want to study the same relation. So suppose I want to look at the relation between wage and education, And I have two groups of people I'm looking at. I have men and women, I have married and unmarried. So I actually have many groups. I have unmarried men and married men. I have unmarried women and married women. So I have these four groups in my data. And for all of them, I want to look at the relation between wage and education. The use of dummy variables is that I can separate out all these groups and separately tell you that it is separate for each of the groups. That is the usefulness of dummy variables. Now, before I look at some data, let me look at those lines. So you see, regression lines are going to haunt us all the time. So you see, ultimately when I'm running a regression, what am I doing? Ultimately, when I'm running a regression, I am estimating a straight line relation between two variables. Okay. So suppose the variables are education and wage. Okay. So my dependent variable is wage and my explanatory variable is education. And suppose now I have estimated this model. So I have estimated a model where I regressed wage on education and on a variable called female, where female is a dummy variable. So female takes 1 if the observation is female, it is 0 otherwise. Okay. So I'm telling you what you are doing when you are including a dummy variable in your regression. You are actually allowing for two separate regression lines. One for men and one for women. So here, what are you saying? So look at my dummy variable. The dummy variable is 1 if it's a woman, okay? And the dummy variable is 0 if it's a man. How do I know that? You know, I always follow this convention. Always give the name of the dummy variable to whatever is 1. I will never ever call a dummy variable gender. Why? Because then I'll have to think about it. Achha, gender. Which one was 1? Which one is 0? I don't like to waste my time. I will straight away take which is the category for which it is 1, which is the category for which it is 0, and give it that name. So female immediately tells me it's 1 if it's a woman, 0 otherwise. So if you have run this kind of a regression where you're regressing the dependent variable on one dummy and one explanatory variable, what are you doing? You're actually regressing two separate, you're actually estimating two separate lines. One for men and one for women. Now here we use a term. Whatever is 1 is our dummy group and whatever is 0 is known as our base group. Okay. So I see that for the base group, in this case the base group is men. All right. For the base group, the intercept of the regression is beta naught. So this is the line for men. You can see this is beta naught. This is the intercept for the, this is the intercept. This is the intercept for the men. Okay. So this is the line for men. And what about for women? For women, the line is beta naught plus delta naught. What is delta naught? Delta naught is the coefficient of the dummy variable. So again, what have you done? You have regressed wages on a dummy, female, and on education. Education is years of education. There are two groups in your data. There are men and there are women. And the dummy female takes the value 1 for the women. It takes the value 0 for the men. Now, when you have estimated such a model, you will get some coefficients. You will get what? You will get all the hats. You will get beta naught hat. You will get delta naught hat, and you will get beta 1 hat. And what are those giving you? So let's look at that. Beta naught hat is telling you that the intercept, the wage regression, in the wage regression on education, the intercept for men, the base group, is beta naught hat. And the intercept of the female, the coefficient of the female dummy is actually the difference between the intercept for the male and the female group. What is the female intercept? The female intercept is beta naught plus delta naught. The intercept plus the coefficient of the dummy. So then what is this difference? The difference in the intercept? This is delta naught. So clearly in this case, delta naught is negative. Delta naught is negative. So the female intercept is less than the male intercept. So we are actually looking at something that's pretty simple. You have run a regression of wage on a dummy female and an explanatory variable male. Look at what you are getting. What you are getting is the intercept term in this regression is actually giving you the intercept of the male regression line. And the intercept of the dummy variable, the intercept of female, is giving you the difference between the male and the female intercepts. Okay, that is the way to interpret the results. So we'll see that this is actually telling us the difference in average wages between men and women is delta naught. That's what this actually represents. Now also note that the line for men and the line for women are parallel. In this model, the slope is the same. So I'm saying by estimating this model, I'm saying that men and women have exactly the same returns on education. An extra year of education gives the same extra wage to men as to women. That is what we are getting through this model. Okay. Now, this is not the only thing that we can do using dummy variables. We can actually allow the male and the female regression lines to be totally different. How? Let's look. So, ouch. Oh dear. Sorry. So I just see we can also allow it to be different. Hang on. I may have, no, sorry, I just open the slide and I'll just show it to you. Hang on, okay? So the male and the female regression lines can actually be completely different in the following sense. So sorry for that glitch, I had not copied it correctly. So you can actually also use dummy variables and allow for all of these cases where the line for men and women not only have different intercepts, but they also have different slopes. Okay. That is also completely possible. In that case, you will have to include what is known as a dummy interaction term in your model. So if you want to, let's say, allow for this case, then what is the kind of model that you will have to estimate? Now, the model that you will have to estimate must include the intercept beta naught plus beta 1 into education, right? Plus delta naught into female. Oops, yeah, delta naught into female plus delta 1 into female into education. Female multiplied by education. Okay, plus the errors. So I can see questions are coming up. Again, I will take questions towards the end of the session. All right, because we have quite a bit of ground to be covered. So again, I will request you to note your question. Please don't worry. I'll answer your questions. Okay. Right now, just listen to what I'm saying. Then I will certainly get back to you and answer the questions. So look at what kind of a model has to be estimated when you are trying to allow for a difference between the slope and the intercept of the regression lines for the two groups in your data. So you have a data set on wage, on education, and you have another dummy variable called female, where female takes 1 for all the women and 0 otherwise. Okay, imagine a data set. Using this data set, if you want to separately estimate a regression line for men and women, which are completely separate lines, the lines have different intercepts and the lines have very different slopes, as in these cases. Then what will you have to do? You will have to estimate this kind of a model. A model where you include the explanatory variable, education, you include the dummy variable, female, and you have to now generate a new variable. A variable which is a multiplicative term. A variable which multiplies the dummy with your explanatory variable. This is a interaction, interaction is another word for multiplication. So this is a new variable that you will have to create. You will have to interact or multiply the dummy with your explanatory variable, create this variable, and then run the regression. Once you have done that, then you will see that you have done exactly what you wanted to. In this model, the beta naught hat is the intercept of the male regression line. The delta naught, so the delta naught is going to be an estimate of the difference in the female minus male regression lines. Okay, so to get the female regression intercept, all you need to do is add beta naught and delta naught, period. What about beta 1? Beta 1 will give you the dy dx for men, the base group. What about delta 1? Delta 1 gives you the difference in the slopes. So delta 1, once you have estimated this model, delta 1, what is delta 1? Delta 1 is the coefficient of the interaction term. The interaction of your dummy with the explanatory variable. Interaction of female into education. It gives you the difference of dy dx for the females minus the dy dx for the males. Okay. When you have estimated this kind of a model, you say that my model has a intercept dummy and a slope dummy. Where is the intercept dummy? So female is your intercept dummy. And where is your slope dummy? So this female into education is your slope dummy. This is a model with an intercept dummy and a slope dummy, where the names come from the fact that the coefficient of the intercept dummy is looking at the difference in the female versus male intercepts. So it's the intercept of the female line minus intercept of the male line. Intercept of the dummy group minus intercept of the base group. That difference is being captured by the coefficient of your intercept dummy. That's why it's called an intercept dummy. Okay. And which is the slope dummy? So this is the slope dummy. Female into education is actually your slope dummy, right? So once you have looked at the coefficient of the slope dummy, which is your delta 1, it's called a slope dummy because it's actually giving you the difference between the slopes. The difference between which slope and which slope? Dummy slope minus base slope. Here my dummy is female. 1 if female, 0 otherwise. Dummy group is female, base group is male. So delta 1 is giving me the difference between the female group, female slope and the male slope. So suppose I see that delta naught is positive and I see that delta 1 is negative. What is that telling me? Remember, delta naught is difference in the averages. So it is telling me that at one level, if you look at people with 0 number of years of education, then the male slope, the male intercept, delta naught, is higher than the female intercept, okay, which is delta naught plus beta naught plus delta naught. Sorry, this is wrong. So I'm talking about interpreting the coefficients of your dummy variable, and then I'm asking, suppose you get delta naught positive. What is delta naught? It's a difference in intercepts. It is the coefficient of your intercept dummy. So delta naught is actually this little bit over here. So the female intercept is this bit, and this is the male intercept. So the female intercept is beta naught plus delta naught. Clearly, delta naught is negative. Oh, sorry, this is sorry. So delta naught is negative. Okay. Okay. So so in other words, let me come back to this with some examples. Perhaps it's going to be clearer then. If you are having some issues understanding, I don't blame you. This is a little complicated, but I'll come back to this. Here, I just want to make the point that if you have run a regression on a dummy explanatory variable where you have put in the dummy explanatory variable as well as a dummy interaction, that is an interaction dummy as well as a intercept dummy as well as a slope dummy, the coefficient of the intercept dummy measures differences in the intercepts of the dummy group minus the base group, and the coefficient of the dummy interaction term or the slope dummy measures the difference in the slopes of the dummy group minus the base group. So in this case, the differences will be female minus male. Female intercept minus male intercept is delta naught, and female slope minus male slope is delta 1. Okay? Okay. Now, let me now come to some data and talk about the dummy variable trap. Okay. Right. So here is the data set that I was actually referring to. Here is a data set where I have data on wages, education. So this is a multiple regression model. So I have more than one explanatory variable. Wage is my dependent variable. So wage is Y, and this is X1, this is X2. So X1 is education, X2 is experience, X3 is age. This is a cross-section data set, and I have lots of observations, and the data looks like. Now, I have a nominal variable called gender, which tells me it's a nominal variable, it's a string variable. So it's just telling me female, male, female, male. Problem is that I can't use this in a regression. And that's where a dummy variable really helps. I define a dummy variable called male. Okay. Male takes the value 1 for all the female it takes the value 1 for all the male observations. And it is 0 for all the female observations. Do you see? Okay. I like to name my variables in a way so that I know exactly which is the dummy group. That is, which is the group for which the variable takes the value 1. Now, I have defined another dummy variable called female, where female takes the value 1 if the observation is a female. So female is in green, and it takes the value 0 for all the males. So is this clear? So the principle is, if I have two groups in my data, male and female, I have defined two dummy variables, one male dummy and one female dummy. Okay. Now here, I also have another nominal variable called race, which is saying white or non-white. This is in the context of the US. And of course, in these days of Black Lives Matter, we know that there's a lot of discrimination in labor market also against the non-whites, potential discrimination. And this data set actually is from that context, can be used to test that hypothesis. So this is race is a nominal variable, which again I can now turn into a dummy variable. I can define two dummies, white, which is 1 for whites, 0 for non-whites, and I can define in green non-white, which is 0 for all the whites and which is 1 for all the non-whites. So very carefully, please inspect this data set to note that how you can actually define a dummy variable to capture and differentiate between various groups in your data. Okay, that is the point that is meant to be illustrated through this example. Now, what I want you to note is you can define as many dummies as you have groups. So let us look at some other examples. Now, sometimes, you can have data with more than one group. So here I have a data set where I am looking at, so in this data set, I am looking at some data on sales. Okay, for 100 firms, I have the relation between sales and advertisement expenditure. So my dependent variable is sales, and advertisement expenditure is the X variable. And I have a variable called quarter, which is a nominal variable. So what is quarter? Quarter is telling me that in quarter 1, sales is it's $20 million, And in the previous quarter, advertisement expenditure was $3 million for this firm. Now, for another firm, okay, you have Q3 data, which is showing $35 million of sales for $5 million of ad spend. For another firm, you have quarter 2 data and so on. So as I look at the effect of advertisement spend on sales, I can actually add some dummy variables to check whether the quarter matters. Is there a quarter effect? So I can run a regression where y is equal to alpha plus beta 1 into x plus delta 1 into q1 plus delta 2 into q2 plus delta 3 into q3 plus u. So please look, what have I done? I have defined 4 dummy variables. But how many have I put in my model? In my model, I have put only 3 dummy variables, Q1, Q2, and Q3. My model has an intercept term. So this is a general rule. When you have several dummy variables, when you have several groups in your data, make sure that you are always putting in one less dummy variable than you have in your data. So if you have 4 groups, you will put in 3 dummy variables. If you have 2 groups, as in the previous case, male and female, I can generate 2 dummy variables, but I'll never use them together in my regression. I will only put in 1 in case my model has an interceptor. Okay? Why is that? This is because of a problem called the dummy variable trap. So let us now look at the X matrix, which I've been talking about for some time now. Let us look at the X matrix to understand what is this dummy variable trap actually all about. Okay, so that is what I'm now going to do. I'm going to talk about the X matrix, which basically has to do with the fact that when I have a multiple regression model, I can express it. The model can be written in terms of a matrix notation. Okay, so the model can be written out in the form of matrices, and it is in that context that I'm talking about the X matrix. So once I discuss the X matrix, 2 things should be clear. One, why is it that we rule out perfect collinearity as an assumption, by assumption, in a multiple regression model? That's one thing that should be clear. The second thing that should be clear is what is the meaning of a dummy variable trap? Okay, so let us now switch to some theory. Let us look at how we can express our model in terms of matrix notation, so that we understand what is the X matrix. Okay. Okay. So in matrix notation, my multiple regression model can be written out as follows. Okay. So in terms of matrices, okay. Sorry. Oops. Yeah, just a moment, please. Yeah. So in terms of matrices, the multiple linear regression model can be written out as y is equal to x beta plus u. What is this? So we just go on to see that y is a vector of dependent variables. X is a matrix, that's our X matrix. Beta is also a vector. U is also a vector. So let us see these things. So when I'm writing out in matrix notation, Y is a column vector. Okay. And then the errors is also a column vector. Okay, these are the errors. And so beta is known as the coefficient vector. So beta is also a column vector. Okay, we'll look at beta, alpha, beta 1, beta 2, etc. So to just take you down, I can write out my model which has k explanatory variables and n observations in terms of matrix notation. Here are my n observations on the dependent variable right here. So y1 is the first dependent variable, yn is the nth dependent variable, the nth observation on the dependent variable. Sorry. So y1 is the first observation, yn is the second observation, giving us an n by 1 column vector. Now, the errors are also a column vector, n by 1 column vector. U1 is the first disturbance, un is the nth disturbance or error. What about beta? The betas are also a column vector. Okay, so the betas are, sorry, so the beta is a the beta is a row vector. It is k plus 1 rows and 1 column. Okay, so this is, I'm sorry, a bit of a mistake. So beta is actually a row vector which has k plus 1 rows. Okay, the first row is alpha, which is my constant term, and beta 1 is is the first slope. Beta k is the kth slope. So I just want to point out that this is not a column vector. This is a row vector. Okay. Now, having said this, how can I write my model as in matrix notation? Note, in matrix notation, I can write this as y is equal to x beta plus u, where u is this particular X matrix. Okay. So what is the X matrix? The X matrix, the first column of the X matrix is a column of 1s. Okay. So think about your beta vector. Beta is like this. Alpha, beta 1, beta 2, dot, 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 up to beta k. Right. And you're writing your model as k by 1. So 1 by k by, yeah. So this has to be 1 into, sorry, 1 second. Huh? So k by, sorry, so this has to be one minute, okay? Just. So this is basically k plus 1, okay, into 1. This has k plus 1 columns and a single row. Okay, so that these are amenable to matrix multiplication. So look at what the X matrix is giving you. The X matrix, each column are the n observations on the variables. So the first column are the n observations on the first variable x1. The kth column is the are all the observations on the kth variables. And essentially, by matrix multiplication, we have to multiply this row with this column. You know, I think I'm just making a small mistake so far as the dimensions are concerned. So far as the dimensions of the vectors are concerned. But basically, the point I want to bring out is that the X matrix has a column of ones, and the X matrix is giving you the full data range in terms of all the variables and all the observations, all the X variables and all the observations. Okay, all right. Now, why am I talking about the X matrix? So let me just show this to you once again. I have y is equal to x beta plus u, where x is a n by k plus 1 matrix and beta is a k plus 1 by 1 vector. So the dimension of beta 1 is k plus 1 by 1. Okay, and I'm multiplying x by beta. So x is the matrix and k is the vector, and they are amenable for matrix multiplication. So look at what beta is all about. Beta is actually giving you so k plus 1. So beta is actually giving you alpha, beta 1, and so on up to beta k, so that the first row of x will be multiplied by beta. This is correct. Okay. Sorry for that little mess up. This is correct. So I realize it's 1:30, but since we started 10 minutes late, I will go up to 1:40 and then I will take some questions, and then I will try to answer as many of your questions as I can. So
Okay,
what I'm trying to do now is I'm trying to talk about the so I'm trying to talk about the I'm trying to talk about the dummy variable trap. Now the answer to why there is a dummy variable trap lies right here. It lies in your understanding of the fact that we can present our multiple regression model in matrix notation as y is equal to x beta plus u, where x is this particular matrix, which has a column of ones. Why is this column of 1 over there? Because the 1 needs to pick up the alpha. It needs to pick up the interceptor. What does this have to do with the dummy variable trap? Suppose, okay, now suppose to understand the dummy variable trap, now let me go back to the data. Let me go back to my slide and ask you the following question. Okay, suppose I were to actually do the following thing. Okay, suppose I were to include both men and women inside my model. Okay, what will happen? To see what will happen, I want you to do something. Just add male and female together. Add these two variables. What will you get? 0 plus 1 equal to 1. 1 plus 0 equal to 1. Do you see that if I add these two variables, then what I will get is a column of ones. So, same thing, white plus non-white. If I have two groups in my data, and if I have two dummy variables defined, and if I add both of them, then what will I get? I will get a column of ones. Okay. Look at the same thing with this other data set with all this Q1 and all that stuff. Okay. If you add up Q1 plus Q2 plus Q3 plus Q4, what will you get? You will get 1. Again, you will generate a column of ones. Appreciate this point. Please appreciate this point because this is fundamental to your understanding of dummy variables, the dummy variable trap. When you have data with multiple groups, you can define multiple dummies. But defining dummies doesn't mean putting them in your model, especially if the model has a constant term. So if you have a constant term, do not put in all the 4 inside the regression model. Do not put in male and female together. Do not put in white and non-white together. Include only one. Because if you don't do that, and if you put in both male and female together, then guess what will happen? Okay, what will happen? You will get a column of ones, and what problem does that cause? Come back to my X matrix. So, my X matrix already has a column of ones. Right? So, I'll just use my cursor. Do this. So look at my X matrix. It has this column of ones. Now, if you have in addition put in 2 dummy variables, those 2 will also add up to 1. So you will have 2 columns of a matrix adding up to a 3rd column. And that is a very problematic case because then what is happening is your you see the condition of linear independence of the rows and columns gets violated. You will be violating the condition of linear independence of rows and columns of the X matrix. So again, please realize your X matrix has a column of ones. Why does it have that column of ones? To pick up that constant term which is there in your model, to pick up that alpha. That's what that column of ones is doing. In addition, you have put in male and female, white and non-white, all the 4 quarters. If you have done this mistake, then you will see that you have landed in a dummy variable trap. Your model cannot be estimated. One of those variables will get dropped. Okay, right. So, what is happening? Why will one of the variables get dropped, and what is this dummy variable trap? The dummy variable trap essentially refers to the fact that if I have 2 groups, male, female, I put in both in my data, then the X matrix has a column of ones and it has 2 more variables which are also adding up to that column, so that the columns are no longer linearly independent, which means the matrix cannot be inverted. X matrix cannot be inverted. If X matrix cannot be inverted, then look at what will happen. There will be no beta hat. Because in matrix notation, beta hat, which is a solution to my alpha hat, beta hat, etc., which is the solution to my system of equations in matrix notation, is this. It is x prime x inverse x prime y. So x prime is basically transpose, right? Transpose. Now, I'm sorry if some of you are there who don't have training in basic matrices. If you plan to use regression model as part of your research, there is no substitute. You'll have to learn matrices. So I'll give you a reference. I'll give you a good reference for learning about it. But for the time being, I'm sorry if this is something that is not familiar to you. There's no other way of understanding the dummy variable trap. So, so you see, the dummy variable trap is occurring because this condition of matrix inversion fails. And the condition of matrix inversion failing would mean that I do not have a solution to my beta hat. I cannot estimate my model. Okay. So that is the whole point about the dummy variable trap. And exactly the same reason why we cannot have perfect collinearity in our model. If we have two variables in my model which are perfectly collinear, then suppose it is the case that there's perfect collinearity between x1 and xk. What does that mean? It means I can express one variable in terms of the other. That is what it would mean. Which means that the two columns of the X matrix are becoming dependent. And if that becomes, if that happens, if two columns are becoming dependent, then there's going to be a grave problem. The grave problem being that I will not be able to invert the X matrix, right? If inverse of the X matrix fails, if I cannot invert the X matrix, then the system of equations will not have a solution. The system of equations being represented by the n observations. So y1 equal to alpha plus beta 1 x1, da, 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 da. Y2 equal to beta 1 plus beta 2, da, 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 da. So those are the n observations. That is your system of equations. And you are using the system of n equations to estimate k plus 1 unknowns. What are the k plus 1 unknowns? Alpha, beta 1, beta 2, beta 3, beta k. That is why the degrees of freedom of the regression is n minus k plus 1. Why freedom? Because you are free to use any of these n. You have more. N is higher than k, right? So you have this many equations. You have n equations to actually estimate k plus 1 unknowns. Okay. So if some of you are losing this because you are not familiar with matrices, I will, as I said, give you a reference. You have to learn this. There's no other way. Okay, if you want to do regression, you have to learn all this. Okay. Right. So where are we? So let me now take you to Stata and let me show you some dummy variables. Okay. So then I told you I would show you Stata and I will do that. Okay. All right. So, what I will do is, you see, I think if I close Stata, I may not be able to open it again with the zoom on. So I'm not closing Stata. Opening Stata is very easy. You just double click and the icon and this whole dialog box is going to open. Okay. The dialog box that you see on my screen, that is going to open when you double click and you open Stata. Okay. All right. So now, once you have opened Stata, what can you do? You will have to get some data into Stata and then start running regressions. Now, the simplest way to do that is actually to copy and paste from Excel. So if you have the data in Excel format, all you need to do is copy the data from Excel and paste it to the Stata data editor. So I will do precisely that. Okay. I will go to Excel. And once I have gone to Excel, I will open a multiple regression data file which has dummy variables. So this has dummy variables and I'm going to copy the full data set with variable names, everything. I'm going to go Control C, copy. And then I will go to Stata. Now, once I'm in Stata, what do? I will open the Stata data editor. Where is the Stata data editor? Please look at the top of your screen. Okay, this is where I will find the Stata data editor. Now you see, if you lightly take your cursor and you hold it over here, you will see it also shows it. So yeah. So this is the Stata data editor, the one with a little pencil on it. And the other one, which has a magnifying glass, is the browser. Okay. So magnifying glass, the one I'm now circling, is the browser. Okay. We don't paste the data on that. उसमें सिर्फ देखने का है. It's just to browse, not to paste. So I will paste my Excel dataset onto Stata to create a Stata dataset by clicking on the data editor, Stata data editor. So what will I do? I will double click on the editor and the editor will open. Oops. Yeah. So the editor has opened. And I will now go Control V. So this is just the command. Control V is the paste. And Stata asks, is the first row as data? I say yes, first row as data. Okay. I don't know why it's giving me an error. But for some reason, it's giving me an error. Maybe I made a mistake copying the data set. Okay. So one moment, I'll just try it once again. Okay. So, you know, this may have something to do with the Excel file itself. The Excel file was actually saved in an old version of Excel, and that is why I may be getting an error message. Okay. So I will just type clear and the data goes away. Treat first row as variable names. Yes, sorry, I had a mistake. When I told treat first row as variable names, it has now given the data. Okay. So I have now closed the editor. So now I have actually pasted the data from Excel to Stata in the Stata data editor. Having done this, my first task is to save it. How can I save this data now as a Stata data file? I will go to File and then I will do Save. Okay. When I do Save, it will open a dialog box and I will just say Test. Okay. Test, and I will save it in some folder. Now please see, it is saving it as a DTA file. It is saving it as a Stata data file. Now my data is saved. How do I know that? Because it is giving me this message. You can see the message on the screen that it has created this particular file and it is saying saved. Now here is something for you. Stata works with the data in its memory. It doesn't keep showing you everything. All right, but it is all there. If you want to see, you just click on browser and you will be able to see the data. Now the good thing about browser is that you cannot change the data by mistake. In browser you can only see us. You can't do anything else. Now in this data set, I have a variable called female. Now let me generate a variable called male. Okay, where the variable called male is something which will take the value 1 if it's a male observation and female and 0 otherwise. So I'll just show you what I have done. So I will just browse male and female. Okay, sure. So do you see? I use the generate command in Stata to generate a dummy variable called male. So male takes the value 0. On your screen, you can see both male and female. Male takes the value 0 whenever female is 1. Because if it's 1, it's a female observation. And whenever female is 0, male takes the value 1. So I am now ready to fall into the double variable trap. Okay. Right. So I have 2 groups in my data, male and female, and I have 2 dummy variables. I have a dummy variable called male and I have a dummy variable called female. So now suppose I regress wage on both of them, male as well as female, and of course on education. So I'm going to regress wage on education, male and female. Look what happens. I'm getting a message saying female is omitted. This cannot be run. Okay. Because there is a dummy variable trap. You cannot put male and female together in one model. But if you put only one variable, there is no problem. So you regress wage on education. So you regress wage on education and male. And there you go. Fine. Now suppose you want to regress wage on education and female. There you go. No problem. So along with looking at the dummy variable trap, I think you've also learned how to regress. You have also learned how to run a regression with Stata. The command is reg, and the first thing after the command reg is the name of your dependent variable, followed by the list of your explanatory variables. And then Stata will show you the results. Okay, now I have really run past my time. So let me get in touch now with the organizers. Please tell me, Anjali G, what are we doing about time? I mean,
Ma'am, you need some more time or like?
I need some time to answer the questions and
Ma'am, you can take, ma'am, let's have a quick, you just scroll to the question answer box and ma'am, we can quickly answer the questions.
yes.
Because the communication is not good enough if we do not answer the queries, ma'am. Thank you, ma'am.
Yeah, so in fact, you know, let me do that. Let me now call it a day over here. And I'm
Yes,
sure in the process of answering your questions, I will be able to make
yes,
some.
ma'am. Yes, ma'am. It will take 10-15 minutes. It's okay, ma'am. Okay,
So
ma'am.
now I'll now start answering the questions. So
Yes, ma'am,
please
please.
put your questions on the chat. I will look at the chats and I will answer them. I will look at the latest chat and then I will scroll up
Yes,
because, you know, that might be the most efficient.
Thank you, ma'am.
You're welcome. Yeah, I'm sorry, my dear participants, that I have not taken your questions so far because I really felt let me get to some material across and then. Okay. Okay. When do we take an interaction term in the regression equation and when not? So, Monica Seni, I'm beginning with your question. So, you're asking me that when do we actually have a interaction dummy versus when we just have a when we just have an intercept dummy. So so far as dummy variable is concerned, we keep an interaction dummy when we want to say that the two regression lines have different intercepts as well as different slopes. That's when we keep an interaction dummy. When we want to say that you have two regression lines with the same intercept but different slopes, you just have an intercept dummy. You don't have a dummy interaction. Okay, this is specific to dummy variables. Now, sometimes we have a model where we are keeping x1, x2 and x1, x2. When do we do that? We do that when we want to say that the marginal effect or the dy dx, when dy dx1 depends on x2. So when you want to say that change in x1, its effect on y is a function of some x2, if you want to allow for that possibility, then you keep also an interaction term in your model. Okay? Okay. All right. That was Monica's answer. Thank you, Rachita. That's so sweet of you to say this. Wajida, Monica, I hope that answered your question. I talked about interaction term in the regression equation because that allows you to, capture the fact that the effect of x on y is a function of a third variable. So, Monica, to answer your question, the best place is chapter 6 of Woolridge. For every researcher, take hold of Woolridge, which is the basic book I would recommend. Introductory macro econometrics. Chapter 6 of Woolridge on functional forms is a must read for every researcher. Whether you're doing economics, business, it doesn't matter. Read it. It's lucid, it is wonderful. Okay. Please explain why the coefficient of male and female dummy are same with opposite signs. I will tell you, Anonymous, when I come to the results. Okay, I'll just come to the. Okay, let me take that. So you see, the male dummy is giving the difference between male minus female, right? And it is positive because the male slope is higher than the female slope. And what is the female slope giving? The female slope is giving the difference between female minus male. So the magnitude is the same. Both of them is, one is 2.27, the other is also 2.27, but the difference, the signs are different because it's just opposite. One is male minus female, male is higher, so it's positive. The other is female minus male. So female is higher, so it is negative. Okay, so to the Anonymous, your question, why the coefficients are same in magnitude, opposite sign, that's the answer. Vajida, when we are studying intergroup differences, please explain how we can use dummy variables. My dear, that is what I did. So you use dummy variables by, basically if you are doing intergroup differences, regress y on x's, all your x's on the dummy or the dummies, and interact the dummies with all of the explanatory variables. So Vajida, for you, chapter 7. Chapter 7 Woolridge is wonderful for dummy variables. Okay, wonderful explanation, beautiful examples. Okay, so introductory econometrics by Woolridge, chapter 7 for dummy variables, chapter 6 for functional forms. Can we apply multiple regression analysis to personality psychology? Okay. Spurti, you see, in psychology and all, when we are looking at all these variables, the problem is that many of them are scaled variables. So, they'll be on a scale of 1 to 5. Yesterday, Dr. Vijay Lakshmi also asked something like this. So I don't know if you're there, Dr. Vijay Lakshmi, but this is also an answer to your question. Suppose some of our variables are in the form of scales. Okay, 1, 2, 3, 4, 5, or on a scale of 1 to 10. How do we deal with these dummy variables? Why? Because you see, suppose I take such a variable and then I'm regressing y on such a variable. You see, to say a unit change does not make sense. A unit change of a scaled variable is very different when it's a change from 1 to 2 versus when it's a change from, let's say, 4 to 5. So you cannot just put these variables in your regression and start interpreting them. Don't do that. Okay. Create groups. The groups will come from your theory. Suppose 1 to 2 bond ratings. 1 to 2 is very good, 2 to 3 is okay, and anything above 3 is, let's say, very bad. Then I'm going to create 3 groups using dummy variables. Good, 1, 0. So it's 1 if it's good, 0 otherwise. Another group, okay. 1 if it's okay, 0 otherwise. Another is bad. 3 groups. 1 if it's bad, 0 otherwise. Do you see? Again, Woolridge chapter 7. Woolridge chapter 7 takes you through this. How, when you have ordinal scale variables, how you can use dummy variables to define groups and then use them in your regression. Okay. Okay, now Logit. Logit, you will have a session on Logit Megha when your question will be answered. Can't we attain research objective? It depends on what is your objective, Azra. If you think there are, so let's say labor market. So labor market, if you are going to say I will ignore dummy variables, I don't think that's a good idea, because labor market is not uniform. A labor market discriminates across groups. So in many professions, married women are heavily discriminated against. Look at air hostesses. Okay, so if you're looking at the market for of jobs for air hostesses, married women are discriminated against typically because they have constraints and so on and so forth, right? So therefore, you would like to keep groups and use dummy variables to separately extract the coefficients for different groups. That is what I would say. If y is equal to cos of y is equal to d1, d2, how can we calculate d3? Okay, so d3 is the third dummy group, I'm assuming. So look, what is the coefficient of d1 going to give you? The coefficient of d1 is giving you the difference of the d1 group with d3. Coefficient of d2 is giving you the difference of d2 group with d3. That is how. Okay. Now, if you want to look at the coefficient of d3 with d2, just switch your model. So now you regress y on d1 and d3. Then immediately you will get differences of d1 with whatever is the base group. So remember, the group you are leaving out, that is the base group. And always the coefficients are reported as differences. The coefficients are capturing differences with respect to the base group. Okay, so that is what you'll have to keep in mind. And you can always change the base group by changing your dummy, which is why I'm keeping both male and female. Some regressions I will report female dummy, some regression I'll report male dummy depending on what I want to do. Okay. Acha. Can I help with productivity model? Sorry, I don't know. How to conduct, but Dr. Reddy was asking how to conduct linear regression in Excel. Very easy, Dr. Reddy, same way. So remember how we did, so I'll quickly, Dr. Reddy, I'll just show you. I'll just show you how to do it in Excel. Very, very easy. So let me just go to Excel. Okay. And here you are. So here is one Excel data set. So you have all these variables and you want to do a regression of multiple linear regression in Excel. What will you do? You will go to data analysis. In data analysis, what will you do? You will choose regression. Now, once you choose regression, it's going to ask for the range of data. So first, it's asking for the dependent variable, input y. So you select that. Ho gaya. Y has been selected. Now input x. Now in place of this 1x, I have several x's. Now make sure there are no gaps in your data. So don't put one blank column. Keep all the explanatory variables together as I have done. Okay. So once you have that, just get hold of all of them and you just say, just select all of them, okay, or specify the data range, and there you are, finish. Very simple. So exactly the same way as you did it for a two variable model. The only thing is that now instead of selecting one column, you select that whole bunch. When you're selecting the bunch, make sure there are no gaps. Very simple. Okay. Right. So where are we? Where are those things gone? Okay, where are those questions? Hello. Okay, oh yeah, I found them. Yeah, here. Okay, okay. Why have you not included constant in dummy regression? We have into Sumanpreet, we included a constant. Whether we are taking only dummy variable values influence. Tinu, I'm sorry, I don't understand. During the interpretation, whether we are taking only the dummy values. No, so you interpret everything. You interpret the coefficient of education as well also, right? So when we are interpreting, I was only interpreting the dummy because that is what I wanted to demonstrate to you, but of course you interpret the others as well. So not just the dummy. Okay. When we are running regression with dummy variable, why we have included constant, you should always keep that constant. You see, if you don't have a constant in your model, you are imposing a constraint. You are saying that let the constant be equal to 0. Let the constant be held equal to 0. So you're moving from unconstrained OLS to constrained OLS, which is not a good idea. So keep the constant in your model. Many things change when you drop a constant from your regression model. By the way, one thing, Stata is very good with self-help also. So let me just point out two things here. One, Stata is menu driven. So if you can see my screen, if you can see Stata on my screen, I'll just show you one thing. So that, sorry. Yeah, so I'll just show you one thing. Yes. So you see, Stata has all these menu functions over here. Now this function statistics, if you open this, it will really take you through and show you what to do. All right, you don't need help. So then if you click on statistics, see it's going to give you all of this. Now somewhere over here, you're going to see, sort of multivariate analysis. There is time series, there is non-parametric, there is, linear models. So inside linear models, you're going to find linear regression, there's linear regression diagnostics, everything is there. So you see, I may not have been able to cover a lot of Stata with you, but at least learn that Stata has a lot of help. And one other thing, suppose you ask for help on Stata, you go to help and then you go to, so sorry, I'll do it once again. You go to help, you go to search, and let's say I search regression, okay? Then it's going to show me something like this. And once I click on this, it's showing me so much help. Now, if I click on this, so let me just point this out. If I click on this blue thing, then it is actually going to give me major help. So here you go. So what did I do? I opened help in Stata, I typed regression, and then I clicked on this thing. I clicked on this first button which came, which is in blue. So if you click on anything in blue, Stata will take you to its documentation. And the documentation, believe you me, is excellent. So here is the Stata documentation now on your screen. You have got help on the regression function in Stata, and if you go through this, I mean, it is just excellent. So you will find a lot of help, and especially under the category called remarks. So if you look at help under the category called remarks, you will see that there is a lot of help using examples and so on and so forth. Okay, so here you go. You will see that, there are lots of examples that have been worked out. So you can see that, there are all these examples which are there. And one more thing about Stata is that Stata has some built-in data sets. So if I tell Stata, okay, to use some of its built-in data sets, so yeah, sorry. Okay, this is creating some problem, but there is a command called sysuse. So there are built-in Stata data sets which can be actually used. Okay, so that is one way to navigate navigate your way through Stata. I just wanted to point out. So in this particular version, the MPG data set is not there, but the help in Stata will surely show you what to do and where to go. Okay. Right. Now, what else is there? Hang on. Are there any more questions? Okay. Right. Okay. Is there a way to correct heteroscedasticity? Okay, yes. Loganathan, I'll just tell you how to correct heteroscedasticity. It'll take 2 minutes, okay? And I'll just do that. Suppose male and female gender after running with a. Thank you. You're welcome. Oh, so sweet. Okay, great. Okay, so I'll just tell you about heteroscedasticity. Now you see, the thing is, heteroscedasticity has such an easy fix that economists have actually stopped testing. Again, I'm talking about economists, but they are a bad lot. They don't look at multicollinearity. They don't test for heteroscedasticity. What do? They assume heteroscedasticity is there and then they fix it. Okay. So mostly researchers who are working with cross-section data set assume that heteroscedasticity is present in the data set. And correcting for heteroscedasticity is so easy that they will correct for it. And how? This is how. I'll just do it. So you can see my screen. Let me run a regression where I'm going to regress wage on years of education and years of experience. Ouch. Sorry. I'm going to regress. Oops, please go away. So I'm going to regress wage on years of education and and experience. Okay, expert. Yeah. So this is a model which may have heteroscedasticity. That's what the economists fear. कि हो सकता है कि इसमें heteroscedasticity है because this is a large cross section data set. How do I fix for it? I just type robust. There you are. So now look, what have I done? I have run a regression first in a model which may have heteroscedasticity. This model can have heteroscedasticity. Anticipating that, I simply fix for it. How do I do that? I simply report a regression where the regression has been done on the basis of robust standard errors. These are heteroscedasticity robust standard errors, which make corrections for heteroscedasticity if it is there. And if it is not there, anyway, the correction is correct. So you see, even if you don't really test for heteroscedasticity, you can always fix it, and you should always do that when you are using a cross section. So look at the beauty of the thing. Using robust errors does not affect your coefficients. The beta hats are the same in the two models. What is different? The difference is in the guys we spent a lot of time familiarizing ourselves with yesterday, the standard errors. So you see the difference in the model that is corrected for heteroscedasticity with the one which is not corrected for heteroscedasticity lies in the standard errors. And therefore it lies in the t statistics, because remember, if the standard errors change, the t statistics will also change. Okay. So that is so far as the heteroscedasticity is concerned. Now I couldn't do quadratics, but quadratics will be there in the slides that I will share. And chapter 6 Woolridge has like loads of things on quadratics. Okay. So the textbook that I wanted to recommend and an easy reading for matrices, let me end with that. The textbook for heteroscedasticity is, and for econometrics is Woolridge. Woolridge. It is an excellent book and I can't praise it enough. Okay, it is a book from where I have learned much, and therefore I would really recommend that you also have a look at it. And it's very easily available. Indian edition is there, so that should not be a problem at all. And Sayyid Rahmatullah, thank you so much. Step-by-step procedure. First step, get hold of Woolridge. And then second step, start reading from chapter 1. Oh, no, not chapter 1. Start reading from the appendix. So that is the second question, okay? That if you want an easy guide to matrices, start with the Woolridge. So Woolridge is kind of like a back to start by reading appendix A, B, C, D from Woolridge. D is for those who want to learn matrices. A gives you basic arithmetics. Where does that help? That helps you interpret your results. Okay. B and C helps with statistics, because you see, econometrics after all is based on statistics. The basis of econometrics is statistics. So to get a recap on all the statistics you need for econometrics, read Woolridge Appendix B and Woolridge Appendix C. Once you have done that, you are on. Now just navigate the whole Woolridge chapter. Half of the book is on cross-section data, which is wonderful. But the half on time series is less wonderful. Okay. So for time series, Enders is better. And, since I have used Woolridge, it tells you why my time series isn't that great. Okay. Anyhow, so that is where, and I think let's call it a day. Okay. Okay. Thank you. Thank you, Anjali. Over to you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Respected Professor Ananya G, Dastidar, my fellow colleagues present here as the panelists, Dr. Purushottam, Mr. Amir is there. It gives me a great privilege to propose a vote of thanks at the conclusion of the 7th day of the 14 days online faculty development program. Ma'am, in last 3 days has given an introduction to regression and in detail enhanced our understanding relating to simple as well as multiple regression. Ma'am has discussed the functional forms and dummy variables in regression using MS Excel, SPSS, and Stata. She has introduced to us to how to deal with the violations of assumptions in regression as well. Ma'am, we are really thankful to you for sparing time for us, and we are honored to have you with us as a resource person. Thank you, ma'am. A lot of compliments and a lot of I can say yeses and wonderful compliments you're getting in the chat box, and we are really thankful, ma'am, for
It's a
sparing
privilege, it's an honor. Let me just tell you one thing. You did not tell me there are going to be so many people. That I would have been really scared. So when I saw that, I was like, what? Okay. But it's great to be able to communicate with so many people through you. Thank you for the
Ma'am, we are still complaining about a lower attendance, and that is what the next announcement I was about to make.
well,
Thank you, ma'am. So it is a blessing in disguise, ma'am.
Okay, thank you.
Thank you, ma'am. Thanks a lot. Thank you. We call it a day now, and I just request all the participants to make sure they are there for the sessions, as we are viewing it that the sessions are not being taken seriously, because otherwise we'll have to resort to taking strict measures to ensure that appropriate amount of attendance is there. Thank you, ma'am. Thank you.
Thank you, ma'am.
Yeah, thank you, Amir.
Dr. Purushottam, can you please close the session?
Okay,
Thank
ma'am.
you.